When we look up at the night sky, we see individual stars scattered across darkness. This apparent randomness hides a deeper truth that astronomers have spent decades uncovering. The universe is not a random scatter of matter, but an intricate tapestry of structures organized across scales so vast they challenge human comprehension. Understanding what constitutes structure in space requires abandoning our terrestrial intuitions about buildings, bridges, and human-made forms. In the cosmos, structure emerges from gravity alone, pulling matter together over billions of years into patterns that repeat across distances measuring hundreds of millions of light years. A structure in astronomical terms means any gravitationally bound or coherent arrangement of matter that persists over cosmological timescales. This definition separates temporary configurations from genuine cosmic architecture. A galaxy qualifies as structure because its hundreds of billions of stars orbit together under mutual gravitational attraction, maintaining cohesion for billions of years. A cloud of gas drifting through intergalactic space does not qualify because it lacks the gravitational binding to persist as a distinct entity. The distinction matters because true structures tell us about the universe's fundamental organization, revealing how matter clumps together rather than spreading uniformly through space. The smallest structures that astronomers consider cosmic architecture are galaxies themselves. The Milky Way spans approximately 100,000 light-years in diameter, containing between 200 billion and 400 billion stars bound together by gravity. Each star orbits the galactic center at speeds reaching hundreds of kilometers per second, yet the galaxy maintains its spiral shape over billions of years. This persistence defines structure. The Andromeda Galaxy, our nearest large neighbor, at 2.5 million light-years distant, demonstrates that galaxies are common cosmic structures rather than unique formations. Observations reveal roughly 2 trillion galaxies in the observable universe, each representing a fundamental structural unit. Beyond individual galaxies, structure emerges through gravitational attraction between galaxies themselves. The local group contains approximately 80 galaxies bound together across a region spanning 10 million light-years. This collection includes the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies, all orbiting their common center of mass. The local group qualifies as structure because these galaxies will eventually merge over billions of years rather than dispersing into cosmic expansion. Their mutual gravity overcomes the universe's expansion, creating a bound system that persists as expansion carries more distant regions away. Galaxy clusters represent the next scale of cosmic structure, containing hundreds to thousands of galaxies within regions spanning tens of millions of light-years. The Virgo cluster, located approximately 54 million light-years away, contains over 1,300 known galaxies, packed into a volume roughly 15 million light-years across. At the cluster's heart sits Messier 87, a supergiant elliptical galaxy containing several trillion stars and harboring a supermassive black hole with mass 65 billion times our Sunday. The cluster's total mass reaches approximately 1.2 times 10 to the 15th solar masses, making it massive enough to gravitationally bind all member galaxies despite their velocities reaching thousands of kilometers per second. The true revelation about cosmic structure came when astronomers mapped galaxy distributions across even larger scales. Instead of finding random scatter or uniform distribution, they discovered that galaxy clusters themselves organize into enormous filaments, walls, and sheets surrounding vast empty regions called voids. This pattern, dubbed the cosmic web, represents the universe's largest scale organization. Filaments stretch hundreds of millions of light-years, containing chains of galaxy clusters, connected like beads on cosmic strings. Walls form sheet-like structures where filaments intersect, creating surfaces tens of millions of light-years across, containing thousands of galaxies. Between these dense structures lie cosmic voids, regions spanning hundreds of millions of light-years containing few galaxies. The Bootes void, discovered in 1981, extends approximately 330 million light-years across, yet contains only 60 large galaxies where thousands would be expected in an average region. These voids are not truly empty but extraordinarily underdense, with galaxy density dropping to 10 or 20% of the cosmic average. The contrast between dense filaments and empty voids creates the universe's foam-like structure, repeated across the entire observable cosmos, spanning 93 billion light-years. Understanding cosmic structure requires recognizing that what we observe today reflects billions of years of gravitational evolution. The early universe, approximately 380,000 years after the Big Bang, was remarkably uniform. The cosmic microwave background radiation shows temperature variations of only 1 part in 100,000 across the entire sky. These tiny fluctuations represented the seeds of all future structure. Regions slightly denser than average possessed slightly stronger gravity, attracting surrounding matter. Over billions of years, this gravitational amplification transformed subtle density variations into the dramatic structures we observe today, from individual galaxies to cosmic filaments spanning billions of light-years. The largest structures challenge our understanding of how matter can organize over such vast distances. Light requires hundreds of millions of years to cross these formations, yet they maintain coherent shapes and patterns. This coherence reveals fundamental truths about dark matter distribution, the universe's expansion history, and the nature of gravity operating across cosmological scales. When astronomers discovered structures exceeding 1 billion light-years, they confronted questions about the maximum size structures can achieve given the universe's finite age and expansion rate. The answers to these questions reshape our understanding of cosmic evolution and the physical laws governing the universe's largest scales. The cosmic web introduction to universal architecture. The cosmic web represents the universe's fundamental architectural pattern, a three-dimensional network of filaments, walls, nodes, and voids extending throughout observable space. This structure was not designed or constructed but emerged naturally from gravitational evolution acting over 13.8 billion years. Understanding the cosmic web means comprehending how simple physical laws, operating across vast timescales, transform a nearly uniform early universe into the rich tapestry of structure we observe today. The web's discovery revolutionized cosmology, revealing that the universe possesses organization on the largest possible scales rather than dissolving into random chaos at extreme distances. Astronomers first glimpsed the cosmic web's existence in the 1980s through galaxy redshift surveys, measuring distances to thousands of galaxies. These surveys revealed that galaxies do not scatter randomly through space, but concentrate along filaments and sheets surrounding enormous voids. The CFA2 Great Wall, discovered in 1989 by Margaret Geller and John Huchra, demonstrated this pattern dramatically. This structure spans approximately 750 million light-years, containing hundreds of galaxy groups and clusters connected in a vast wall-like formation. The wall is not a solid object, but a region where galaxy density exceeds the cosmic average by factors of 5 to 10, creating a coherent structure visible across hundreds of millions of light-years. The cosmic web consists of 4 primary components: each playing essential roles in the universe's structure. Filaments form the web's connective tissue, elongated structures stretching hundreds of millions of light-years, while measuring only 10 to 30 million light-years wide. These filaments contain galaxy groups and clusters strung along their lengths like lights on cosmic cables. The Perseus-Pisces supercluster exemplifies filamentary structure, extending approximately 300 million light-years and containing numerous galaxy clusters connected through the underlying dark matter distribution. Filaments comprise roughly 40% of the universe's matter, while occupying only 10% of its volume, making them the cosmic web's densest components outside galaxy clusters themselves. Walls or sheets form where multiple filaments intersect, or where void expansion compresses matter into thin layers. These two-dimensional structures extend tens of millions of light-years across, while remaining only several million light-years thick. Walls contain galaxy groups and occasional clusters distributed across their surfaces, creating cosmic versions of soap bubble films. The Sloan Great Wall, discovered in 2003, spans approximately 1.4 billion light-years, making it one of the largest known wall-like structures. Walls comprise roughly 20 to 30% of cosmic matter, while occupying 10 to 15% of volume, serving as boundaries between neighbouring voids. Nodes represent the cosmic web's densest regions, formed where multiple filaments intersect. Galaxy clusters invariably occupy these nodes, collecting matter flowing along converging filaments. The Coma cluster exemplifies nodal structure, sitting at the intersection of several major filaments, with total mass exceeding 1 quadrillion solar masses. At nodes, matter flows inward along filaments at velocities reaching thousands of kilometers per second, feeding ongoing cluster growth. The combination of high density and dynamic infall creates extreme environments where galaxies undergo rapid evolution through mergers, interactions, and environmental processes impossible in quieter field regions. Voids fill the cosmic web's remaining volume, occupying 50 to 70% of space depending on definition. These underdense regions span 100 to 500 million light-years, containing galaxy densities 10 to 20% of the cosmic average. The Bootes void exemplifies extreme underdensity, spanning 330 million light-years, yet containing only 60 large galaxies compared to thousands expected. Voids are not completely empty, but extraordinarily sparse, with gas and dark matter present at densities far below average. The few galaxies residing in voids show distinctive properties, predominantly late-type spirals with active star formation, blue colors, and high gas fractions, having avoided the environmental processing affecting galaxies in denser regions. The cosmic web's pattern repeats across the entire observable universe with remarkable consistency. Whether astronomers observe nearby regions within several hundred million light-years or distant volumes billions of light-years away, the same basic structure appears. Filaments connect clusters, walls surround voids, and the foam-like pattern persists. This universality demonstrates that the cosmic web reflects fundamental physics rather than local conditions. Gravity, dark matter distribution, and cosmic expansion conspire to create identical patterns regardless of location, confirming the cosmological principle that the universe appears the same from all positions on sufficiently large scales. Computer simulations reproduce the cosmic web's structure with stunning accuracy. Starting from the density fluctuations observed in the cosmic microwave background, simulations evolve matter forward through cosmic time, using only gravity and expansion. The resulting structures precisely match observed galaxy distributions, filament patterns, and void properties. These simulations reveal that dark matter dominates the web's architecture. Filaments consist primarily of dark matter halos connected through diffuse dark matter streams, with galaxies forming where halos become sufficiently massive. The visible cosmic web traces underlying dark matter distribution, making galaxy surveys powerful tools for mapping the universe's dominant but invisible component. The cosmic web's discovery answered fundamental questions about cosmic organization while raising new ones. Why does the universe organize into filaments and voids, rather than distributing matter uniformly or concentrating it entirely into isolated clusters? The answer lies in gravitational instability's nature. Overdense regions attract matter, growing denser, while underdense regions lose matter, becoming voids. This process operates differently along different dimensions. Collapse along one dimension creates filaments. Collapse along two dimensions creates walls. Full three-dimensional collapse creates clusters at filament intersections. The cosmic web represents gravity's signature across the universe's largest scales, revealing how matter organizes when left to evolve under mutual attraction for billions of years. Galaxies as building blocks, the smallest structures. Galaxies represent the fundamental building blocks of cosmic structure, the smallest units that astronomers consider when mapping the universe's large-scale organization. Each galaxy contains billions to trillions of stars bound together by gravity, orbiting a common center over millions of years. Understanding galaxies as structural components requires recognizing they are not merely collections of stars, but complex systems containing stars, gas, dust, and dark matter organized into distinct morphologies. These systems persist for billions of years, maintaining their identities even as they interact, merge, and evolve. The 2 trillion galaxies populating the observable universe serve as tracers of larger structures, revealing the cosmic web's architecture through their distributions and motions. The Milky Way, our home galaxy, exemplifies typical large spiral structure. Spanning approximately 100,000 light-years in diameter and containing 200 to 400 billion stars, the Milky Way organizes matter into a rotating disk with spiral arms, a central bulge, and an extended spherical halo. The disk rotates at approximately 220 kilometers per second at the Sun's location, 26,000 light-years from the galactic center, completing one orbit every 225 million years. This organized rotation demonstrates gravitational binding that defines the Milky Way as a coherent structure rather than a temporary association of stars. The galaxy's total mass reaches approximately 1.5 trillion solar masses, including dark matter, making it massive enough to gravitationally dominate the local group's dynamics. Galaxies display 3 primary morphologies, each representing different formation and evolution histories. Spiral galaxies, like the Milky Way and Andromeda, contain rotating disks with spiral arm patterns, active star formation, and substantial gas reservoirs. Approximately 60% of nearby galaxies show spiral or irregular morphologies, dominating the population in low-density environments. Elliptical galaxies lack disks and spiral structure, instead forming smooth, featureless ellipsoids containing predominantly old red stars with minimal star formation. These galaxies dominate cluster cores, where mergers and environmental processing transform spirals into ellipticals. Lenticular galaxies represent intermediate types, possessing disk structure without prominent spiral arms or significant star formation, possibly representing transition states between spirals and ellipticals. Galaxy masses span enormous ranges, from dwarf galaxies containing millions of stars with total masses around 10 million solar masses, to giant ellipticals containing trillions of stars exceeding 1 trillion solar masses. The Triangulum Galaxy, the local group's third largest member at approximately 3 million light-years distance, contains roughly 40 billion stars with total mass around 50 billion solar masses. This places it among intermediate mass galaxies, substantial enough to maintain distinct structure while remaining much smaller than giants like the Milky Way and Andromeda. At the opposite extreme, IC 1101, a supergiant elliptical approximately 1 billion light-years away, spans 6 million light-years and contains roughly 100 trillion stars, making it among the universe's largest single galaxies. Dwarf galaxies outnumber large galaxies by factors of 10 or more, representing the most common galactic structures. The local group contains approximately 80 known galaxies, but only 3 qualify as large spirals. The remaining 70+ members are dwarf galaxies ranging from the Large Magellanic Cloud with 10 billion stars to ultra-faint dwarfs containing only thousands of stars barely distinguishable from globular clusters. Despite low luminosity, dwarf galaxies contribute significantly to cosmic structure. Their prevalence means they trace large-scale structure as effectively as luminous giants, and their dark matter content often exceeds luminous matter by factors of 100, making them crucial for mapping dark matter distribution. Galaxies cluster together on scales from small groups to massive clusters. The local group exemplifies small groups, containing 80 members within 10 million light-years. Groups typically host a few large galaxies plus numerous dwarfs, with total masses reaching 10 to the 13th solar masses. The Virgo cluster demonstrates rich cluster structure, containing over 1,300 galaxies within 15 million light-years. Cluster environments dramatically affect galaxy evolution through processes impossible in isolation. Ram pressure stripping removes gas as galaxies plow through hot intracluster medium at velocities exceeding 1,000 km per second. Tidal interactions during close encounters strip stars from galactic outskirts. Major mergers combine galaxies into larger ellipticals, transforming spiral populations into elliptical-dominated clusters. Galaxy surveys measuring distances and positions for millions of galaxies reveal how these building blocks trace larger structures. The Sloan Digital Sky Survey mapped galaxy positions across 1/3 of the sky, measuring redshifts for millions of galaxies out to distances exceeding 2 billion light-years. These surveys show galaxies concentrating along cosmic web filaments and walls while avoiding voids. The galaxy distribution's statistical properties constrain cosmological models, testing predictions about dark matter, dark energy, and structure formation. Comparing observed clustering patterns to computer simulations determines whether models correctly describe how galaxies form and organize into larger structures. Understanding galaxies as building blocks means recognizing they are not static objects, but evolving systems shaped by cosmic environment. Galaxies in dense cluster cores evolve faster than isolated field galaxies, undergoing mergers and environmental processing that transform morphologies over billions of years. Galaxies in filaments experience intermediate environments, occasionally interacting with neighbors while avoiding the extreme conditions of cluster cores. Void galaxies evolve in isolation, retaining gas and maintaining spiral morphologies billions of years longer than cluster galaxies. This environmental dependence makes galaxies powerful tracers of cosmic structure because their properties reflect their locations within the cosmic web. From groups to clusters, gravity builds larger structures. The transition from individual galaxies to galaxy groups and clusters represents the first major step in cosmic structure's hierarchical organization. Groups and clusters are not merely collections of nearby galaxies, but gravitationally bound systems where member galaxies orbit their common center of mass, held together by mutual gravitational attraction strong enough to overcome cosmic expansion. These structures contain anywhere from a few dozen galaxies in small groups to thousands in rich clusters, spanning volumes from several million light-years for compact groups to tens of millions of light-years for massive clusters. Understanding this scale is essential because clusters represent the largest structures that remain gravitationally bound, the maximum size where gravity definitively wins against the universe's expansion. The local group, containing approximately 80 galaxies within 10 million light-years, demonstrates typical small group structure, dominated by two large spirals, the Milky Way and Andromeda, plus the intermediate Triangulum galaxy. The local group's total mass reaches approximately 2 trillion solar masses, including dark matter. The member galaxies orbit the group's center of mass, located between the Milky Way and Andromeda, approximately 1 million light-years from each. Velocities within the group range from tens to hundreds of kilometers per second, insufficient to escape the collective gravitational binding. The Milky Way and Andromeda are approaching at 110 kilometers per second, destined to merge in approximately 4.5 billion years, demonstrating that group members interact dynamically rather than maintaining static configurations. Galaxy groups typically contain 3 to 30 large galaxies, plus numerous dwarf members, spanning regions 2 to 6 million light-years across. The M81 group, located approximately 12 million light-years away, exemplifies typical group properties. This system contains approximately 30 visible members, dominated by 3 large galaxies: M81, M82, and NGC 3077. Observations reveal tidal interactions between these galaxies, with hydrogen, gas, bridges, and tails stretching between them, indicating past close encounters. M82, the famous cigar galaxy, underwent a close passage with M81 roughly 300 million years ago, triggering an intense starburst, forming stars at 10 times normal rates. These interactions demonstrate that groups are dynamically active environments where galaxies frequently encounter each other, driving evolution through gravitational encounters. Compact groups represent extreme environments where multiple galaxies orbit within regions only a few 100,000 light-years across, comparable to individual galaxy sizes. Stephan's quintet, discovered in 1877, contains 5 apparent members spanning only 200,000 light-years, though one member is actually a foreground galaxy not physically associated with the group. The 4 genuine members interact violently, with collision speeds reaching thousands of kilometers per second, producing shock waves visible in X-ray and infrared observations. These compact configurations cannot survive indefinitely. Gravitational encounters exchange energy between members, eventually causing some galaxies to merge while ejecting others to larger distances or even entirely from the group. Galaxy clusters represent the next structural scale, containing hundreds to thousands of galaxies within regions spanning 10 to 30 million light-years. The Virgo cluster, at 54 million light-years distance, exemplifies nearby rich clusters. Containing over 1,300 galaxies dominated by giant elliptical Messier 87, Virgo's total mass exceeds 1.2 times 10 to the 15th solar masses. Most of this mass exists not in stars, but in dark matter and hot intracluster gas. X-ray observations reveal gas heated to 10 million Kelvin, filling the cluster volume, with mass exceeding all cluster galaxies combined. This gas resulted from both primordial gas, captured during cluster formation, and gas expelled from galaxies through supernovae and active galactic nuclei. The Coma cluster, located 320 million light-years away, demonstrates even richer structure, containing over 1,000 large galaxies, plus potentially 10,000 dwarf members within approximately 20 million light-years. Coma's core achieves extreme densities, where galaxies separate by only a few 100,000 light-years. Swiss astronomer Fritz Zwicky studied Coma in 1933, measuring galaxy velocities through Doppler shifts. He found velocities so large that visible matter alone could not bind the cluster gravitationally. Galaxies moved at thousands of kilometers per second, speeds requiring far more mass than observed stars and gas provided. Zwicky concluded that unseen dark matter must exist, providing additional gravity. This marked the first evidence for dark matter, now understood as comprising 85% of cosmic matter. Cluster mass measurements employ multiple techniques, all confirming dark matter dominance. Gravitational lensing, where cluster gravity bends light from background galaxies, directly measures total mass, including dark matter. Observations show that cluster lensing masses exceed visible matter by factors of 50 to 100, confirming Zwicky's hypothesis. The hot intracluster gas detected through X-ray emission provides another mass probe. Gas temperature and density profiles, combined with hydrostatic equilibrium assumptions, yield total cluster masses consistent with lensing measurements. Galaxy velocities provide a third method through the virial theorem relating kinetic energy to gravitational potential energy. All methods agree. Clusters contain far more matter than visible, predominantly in dark matter halos, extending well beyond visible galaxy distributions. Environmental processes in clusters dramatically affect member galaxy evolution. Ram pressure stripping occurs when galaxies move through the hot intracluster medium at high velocities, experiencing wind pressure that sweeps away their cold interstellar gas. Observations reveal galaxies with one-sided tails of gas trailing their motion through clusters, direct evidence of ongoing stripping. Stripped of gas, galaxies cannot form new stars, transforming from blue spirals into red passive systems. Galaxy harassment through rapid close encounters also transforms cluster members. Even without direct collisions, tidal forces during high-speed passages heat galactic disks, puffing them into spheroids. These processes explain why cluster cores contain predominantly red elliptical and lenticular galaxies, while field environments contain mostly blue spirals. The boundary between groups and clusters remains somewhat arbitrary, typically defined by member count or total mass. Systems with fewer than 50 large galaxies are usually classified as groups, while richer systems qualify as clusters. This distinction matters because it separates structures where individual galaxy interactions dominate from those where collective environmental effects through hot gas and strong tidal fields shape evolution. Groups represent environments where mergers build larger galaxies, while clusters represent environments where stripping and harassment dismantle galaxies. Both play crucial roles in building larger cosmic structures, serving as nodes in the cosmic web where filaments intersect and matter accumulates. Superclusters emerge connecting the web. Superclusters represent structures intermediate between individual galaxy clusters and the full cosmic web, consisting of multiple clusters and groups connected by filaments spanning 100 to 500 million light-years. Unlike clusters, superclusters are not gravitationally bound as single units. Cosmic expansion driven by dark energy overcomes their collective gravity, causing superclusters to gradually disperse rather than collapse into single systems. Despite this lack of binding, superclusters represent coherent structures in galaxy distribution. regions where density exceeds cosmic average by factors of several, creating connected networks of clusters and groups. Understanding superclusters reveals how the cosmic web organizes matter on scales approaching the largest structures observable in the universe. The Virgo supercluster, containing the local group Virgo cluster and numerous other groups and clusters, exemplifies traditional supercluster structure. Spanning approximately 110 million light-years in diameter and containing roughly 100,000 galaxies, this structure represents our extended cosmic neighborhood. The supercluster's center lies near the Virgo cluster, with the local group positioned on the periphery approximately 65 million light-years from Virgo. Observations reveal that the local group and surrounding groups are being pulled toward Virgo at approximately 200 to 300 kilometers per second, demonstrating Virgo's gravitational influence despite the structure not being fully bound. This infall velocity represents deviation from pure cosmic expansion, indicating that Virgo's gravity affects dynamics across the entire supercluster volume. However, the traditional Virgo supercluster definition proved incomplete when astronomers analyzed galaxy peculiar velocities across larger volumes. In 2014, Brent Tully, Hélène Courtois, and colleagues revealed that gravitationally, our region belongs to a much larger structure defined by velocity flows rather than density alone. Using peculiar velocity measurements for thousands of galaxies, they mapped how galaxies move relative to cosmic expansion's smooth flow. This analysis identified velocity flow basins analogous to watersheds, regions where galaxies flow toward common gravitational attractors. The local group, Virgo cluster, and numerous other structures all flow toward a common center, defining a single enormous supercluster. This structure, named Laniakea from Hawaiian meaning immeasurable heaven, extends approximately 520 million light-years across, with total mass around 100 quadrillion solar masses, roughly 100 times larger and more massive than the traditional Virgo supercluster. Laniakea's boundaries are defined by velocity flow separatrices, surfaces where flow directions diverge, marking transitions between different attraction basins. Within Laniakea, all galaxies share a common destiny, flowing toward the structure's center of mass, located near the Great Attractor region, approximately 250 million light-years from the local group. Flow velocities reach 600 to 700 kilometers per second for galaxies deep within the structure, demonstrating powerful gravitational influences organizing matter across hundreds of millions of light-years. Laniakea encompasses multiple previously identified superclusters, including the traditional Virgo supercluster, Hydra Centaurus supercluster, Pavo Indus supercluster, and parts of the Centaurus supercluster. These smaller structures, defined by local density enhancements, represent substructures within the larger velocity-defined basin. The Virgo cluster, despite its proximity and prominence, contains only a small fraction of Laniakea's total mass, roughly 1%. Most mass concentrates in more distant regions toward the Great Attractor and Shapley concentration, explaining why our velocity flow points well beyond Virgo toward these more massive attractors. The Shapley concentration at 650 million light-years, though technically outside Laniakea's boundaries, exerts gravitational influence affecting velocity flows within Laniakea, particularly near the boundary between the two basins of attraction. The Perseus-Pisces supercluster represents Laniakea's neighboring structure, defined by its own velocity flow basin. Located on Laniakea's boundary, Perseus-Pisces extends roughly 300 million light-years and contains its own collection of clusters and groups flowing toward its gravitational center. The boundary between Laniakea and Perseus Pisces is not a wall or physical barrier, but a separatrix surface where velocity flows diverge, galaxies on one side flowing toward Laniakea's center, while those on the other side flow toward Perseus Pisces. This boundary demonstrates that superclusters represent dynamic structures defined by gravitational dynamics, rather than static density distributions. Matter continuously flows along gravitational gradients, organizing into basins of attraction that define the cosmic web's largest coherent structures. Supercluster catalogues compiled from galaxy surveys reveal dozens of these enormous structures within several billion light-years. The Shapley supercluster, at 650 million light-years distance, ranks among the most massive known, containing over 25 rich galaxy clusters with total mass exceeding 10 to the 17th solar masses. The Horologium Reticulum supercluster extends approximately 550 million light-years at 700 million light-years distance, containing over 5,000 galaxies organized into multiple clusters and groups. The Corona Borealis supercluster, discovered through analyses of the Sloan Digital Sky Survey, spans approximately 150 million light-years at 1 billion light-years distance, demonstrating that supercluster structures persist to cosmological distances where the universe appears significantly younger than today. Superclusters trace the cosmic web's densest regions, forming at intersections of multiple filaments where matter accumulates over billions of years. Computer simulations, starting from cosmic microwave background fluctuations, accurately reproduce observed supercluster properties, confirming they formed through gravitational amplification of initial density fluctuations. Regions slightly overdense in the early universe attracted surrounding matter, growing denser, while neighboring underdense regions lost matter, becoming voids. This process operated hierarchically, with small structures forming first, then merging into progressively larger systems. Superclusters represent relatively recent formations in cosmic time, assembling over the past several billion years as previously isolated clusters and groups fell together along filaments. The transition from superclusters to even larger structures remains debated. Some structures approaching or exceeding 1 billion light-years challenge our understanding of maximum structure sizes given cosmic age and expansion. The Hercules Corona Borealis Great Wall, potentially spanning 10 billion light-years, raises questions about whether structures this large can form through gravitational evolution within available time. These questions test cosmological models, requiring careful analysis of whether apparent structures represent genuine coherent formations or statistical fluctuations in galaxy distributions. Understanding where supercluster structures end and random statistical patterns begin helps define the maximum scale where gravity organizes matter before cosmic expansion and dark energy prevent further structure growth. Filaments and walls, the cosmic web's skeleton. Filaments and walls form the cosmic web's structural skeleton, creating elongated chains and sheet-like formations where galaxies concentrate while surrounding vast empty voids. These structures represent the universe's most prominent organizational pattern on scales exceeding 100 million light-years, visible in galaxy surveys as coherent features extending across significant fractions of the observable universe. Filaments connect galaxy clusters like cables between nodes in a network, while walls form barriers between adjacent voids like soap bubble films. Understanding these structures reveals how gravity organizes matter in 3 dimensions, creating the foam-like pattern that characterizes the universe's large-scale architecture. Filaments represent elongated overdensities, typically measuring 500 million to 1 billion light-years long, while remaining only 10 to 30 million light-years wide, creating aspect ratios of 50 to 1 or more. The Sloan Great Wall demonstrates extreme filamentary structure, extending approximately 1.4 billion light-years through a region where galaxy density exceeds cosmic average by factors of 5 to 10. Discovered in 2003 by Richard Gott and colleagues analyzing Sloan Digital Sky Survey data, this structure contains hundreds of galaxy groups and clusters connected along its length. Despite spanning over 1% of the observable universe's diameter, the Sloan Great Wall is not a solid object, but a statistical enhancement where galaxy density peaks along a linear trajectory spanning billions of light-years. Cosmic filaments typically contain 40% of the universe's matter while occupying only 10% of its volume, making them the second densest component after galaxy cluster cores. Matter within filaments flows along their lengths toward nodes where galaxy clusters form, with typical velocities reaching hundreds of kilometers per second. This flow feeds cluster growth, delivering fresh gas and galaxies that clusters accrete over billions of years. Simulations reveal that filaments consist primarily of dark matter, with galaxies forming where dark matter halos become sufficiently massive. The visible filamentary structure traces underlying dark matter distribution, meaning galaxy surveys effectively map the universe's dominant but invisible mass component. The Perseus-Pisces supercluster chain exemplifies rich filamentary structure, extending approximately 300 million light-years and containing numerous galaxy clusters, including Perseus, Pisces, and several others connected through the cosmic web. Observations reveal hydrogen gas streams flowing between clusters along the filament, detectable through absorption of background quasar light. This intergalactic gas, heated to temperatures reaching 100,000 to 1 million Kelvin, represents matter in the process of accreting onto clusters, filling the space between nodes. The filament's total mass exceeds 10 to the 15th solar masses, comparable to rich galaxy clusters but distributed across vastly larger volumes, creating much lower average densities. Walls or sheets form where multiple filaments intersect or where void expansion compresses matter into thin layers. These two-dimensional structures extend tens of millions of light-years across, while remaining only several million light-years thick, creating vast surfaces containing thousands of galaxies. The CFA-2 Great Wall, discovered in 1989, demonstrates classic wall structure spanning approximately 750 million light-years across the sky. This formation contains the Coma Cluster, Hercules Cluster, and numerous other groups arrayed across a surface separating multiple voids. The wall is not perfectly planar, but shows complex three-dimensional structure with filaments threading through it, creating a combination of one-dimensional and two-dimensional features. Wall structures comprise roughly 20 to 30% of cosmic matter distributed across 10 to 15% of volume, intermediate between filaments and voids in density. Galaxies within walls show moderate density enhancements and complex kinematics as they fall toward embedded clusters and filaments threading through wall surfaces. The CFA-2 Great Wall's galaxies display velocity dispersions, indicating that the structure is not gravitationally bound as a whole, but represents a transient configuration that will disperse as cosmic expansion continues. Individual clusters within the wall remain bound, but the overall wall structure is merely a density enhancement in the cosmic web rather than a permanent fixture. Mapping filaments and walls requires three-dimensional galaxy surveys measuring both positions on the sky and distances through redshift observations. The Sloan Digital Sky Survey revolutionized this field by obtaining spectra for millions of galaxies across 1/3 of the sky, measuring redshifts that convert angular positions into three-dimensional coordinates. Plotting galaxy positions in 3 dimensions reveals filamentary and wall-like patterns invisible in 2-dimensional projections. The resulting maps show the cosmic web's intricate structure, with filaments stretching between clusters, walls surrounding voids, and a hierarchical pattern repeating across multiple scales, from tens of millions to billions of light years. Computer simulations reproduce filamentary and wall structures with remarkable fidelity. Starting from initial conditions matching cosmic microwave background observations, simulations evolve dark matter under gravity through cosmic time. The resulting distributions show filaments connecting nodes, walls forming void boundaries, and the same foam-like pattern observed in galaxy surveys. These simulations reveal that filaments and walls arise naturally from gravitational collapse proceeding differently along different dimensions. Overdense regions collapse first along their shortest axis, forming walls. Continued collapse along the next axis transforms walls into filaments. Finally, collapse along the third dimension creates nodes where clusters form. This dimensional hierarchy explains why the cosmic web exhibits mixed one-dimensional filaments, two-dimensional walls, and three-dimensional nodes rather than uniform structure. Filaments and walls serve crucial roles in galaxy evolution by channeling matter toward clusters while maintaining intermediate densities where galaxies evolve under conditions less extreme than cluster cores. Galaxies in filaments undergo occasional interactions with neighbors, experiencing moderate environmental effects. This creates populations intermediate between isolated field galaxies that evolve slowly and cluster galaxies that undergo rapid transformation through mergers and stripping. Observations confirm that filament galaxies show properties between these extremes, with star formation rates and gas fractions intermediate between field and cluster populations. This gradient demonstrates that cosmic web location fundamentally shapes galaxy properties, making the web's architecture essential for understanding galaxy evolution across cosmic history. Voids, the empty spaces that define structure. Cosmic voids represent the universe's most voluminous component, occupying 50 to 70% of space while containing only 10 to 20% of galaxies. These enormous underdense regions span 100 to 500 million light-years, with the largest examples exceeding 1 billion light-years across. Voids are not completely empty, but extraordinarily sparse, containing galaxy densities 10 to 20% of cosmic average. Understanding voids is essential because they define cosmic structure as profoundly as the dense filaments and walls surrounding them. The cosmic web's pattern emerges from the contrast between overdense filaments and underdense voids, creating the foam-like structure visible in galaxy surveys. Voids represent the spaces where structure is absent, yet their properties reveal fundamental truths about cosmic evolution and dark energy's effects on expansion. The Boötes void, discovered in 1981 by Robert Kirshner and colleagues, demonstrates extreme underdensity. Spanning approximately 330 million light-years, at 700 million light-years distance, this void contains only 60 large galaxies, where thousands would be expected at average density. Initial surveys found almost no galaxies within the void, leading to the nickname Great Void. Subsequent deeper observations identified additional dwarf galaxies and small groups, but total galaxy density remains below 20% of cosmic average. The void's existence challenges naive expectations that galaxies should distribute uniformly through space. Instead, gravitational evolution concentrates matter into filaments and walls, evacuating voids through billions of years of matter flow toward overdense regions. Void sizes correlate with cosmic environment, with larger voids appearing in underdense regions, while smaller voids fill spaces between filaments in average density environments. The KBC void, named after discoverers Keenan, Barger, and Cowie, potentially represents an even larger example, spanning approximately 2 billion light-years with the local group possibly located near its edge. If confirmed, this structure would rank among the largest voids known, though its existence remains controversial. Some analyses find strong evidence for large-scale underdensity surrounding the local group, while others attribute observed patterns to statistical fluctuations rather than genuine void structure. Determining whether we reside in or near a large void matters for cosmology, because local underdensity would affect expansion rate measurements, potentially biasing estimates of the Hubble constant. Void interiors contain distinctive galaxy populations shaped by the absence of dense environments. Void galaxies are predominantly late-type spirals and irregulars with active star formation, blue colors, and high gas fractions. These galaxies avoided the environmental processing, affecting galaxies in filaments and clusters, evolving in isolation without frequent interactions or gas stripping. Observations reveal void galaxies have lower masses, fainter luminosities, and slower rotation velocities compared to galaxies in denser regions. This suggests that void regions contained fewer or smaller dark matter halos in the early universe, preventing formation of massive galaxies. The few galaxies that did form in voids evolved slowly, retaining their gas and maintaining star formation for billions of years longer than cluster galaxies. Void expansion proceeds faster than cosmic average due to reduced gravitational deceleration. Regions with below average density experience weaker gravitational pull from surrounding matter, allowing them to expand faster relative to denser regions. This differential expansion causes voids to grow over time, with matter flowing outward from void centers towards surrounding filaments and walls. The expansion rate difference is only 1 to 2% faster than average, but accumulated over billions of years, this transforms initial slight underdensities into the dramatic voids observed today. Simulations show that voids began as regions slightly below cosmic average density in the early universe, then expanded as matter flowed toward neighboring overdensities, creating the evacuated regions we observe. The largest voids challenge cosmological models through questions about maximum void sizes. The cosmological principle states that the universe should appear homogeneous and isotropic on scales exceeding approximately 300 million light-years. Structures larger than this should not exist because insufficient time has passed since the Big Bang for gravity to organize matter on such scales given the universe's expansion. Yet voids exceeding 1 billion light-years have been identified, approaching or potentially exceeding this homogeneity scale. Either these structures represent statistical flukes, rare but allowed fluctuations in matter distribution, or something about structure formation is incompletely understood. The existence of large voids provides tests of cosmological models, constraining dark energy properties and structure formation physics. Voids serve as cosmological laboratories for testing dark energy models. Dark energy drives accelerated expansion, which affects void growth differently than it affects dense region evolution. Faster acceleration enhances void expansion, increasing their sizes and underdensity contrasts. Slower acceleration suppresses void growth. By measuring void sizes and expansion rates at different cosmic epochs using galaxy surveys, astronomers constrain dark energy properties. Different dark energy models from constant cosmological constant to dynamically evolving quintessence, predict different void evolution. Observations of void statistics from nearby regions to high redshift provide independent tests of dark energy, complementing supernova distance measurements and cosmic microwave background observations. Void shapes provide additional cosmological information. If dark energy behaves as Einstein's cosmological constant, voids should be roughly spherical because expansion is isotropic. If dark energy has directional properties, or if the universe's geometry is non-standard, voids might display preferred shapes or orientations. Surveys mapping void shapes across large volumes find predominantly spherical or mildly elliptical voids, consistent with isotropic expansion and standard cosmology. This agreement supports the cosmological constant model while constraining alternatives. Void shapes also test general relativity on cosmological scales, as any deviations from Einstein's theory would affect how voids grow and evolve through cosmic time. The void filament contrast creates one of astronomy's most striking patterns. Maps showing galaxy distributions reveal bright filaments and walls surrounding dark voids, creating bubble-like structures resembling soap foam. This pattern extends across the entire observable universe, visible from nearby regions within several 100 million light-years to distant volumes, billions of light-years away, where the universe appears as it was billions of years ago. The pattern's consistency demonstrates that cosmic structure formation follows universal laws rather than local conditions. Whether we observe nearby or distant, young or old universe, the same basic structure appears: matter concentrating into filaments and walls while evacuating voids, creating the cosmic web's characteristic foam-like architecture. The Sloan Great Wall, a billion light-years of structure. The Sloan Great Wall stands as one of the largest coherent structures ever mapped in the universe, extending approximately 1.4 billion light-years through a region where galaxy density significantly exceeds cosmic average, discovered in 2003 by J. Richard Gott and colleagues analyzing data from the Sloan Digital Sky Survey. This enormous formation challenges our understanding of how large structures can grow given the universe's finite age and expansion rate. The Sloan Great Wall is not a solid object, but a statistical enhancement where galaxy counts peak along an elongated trajectory containing hundreds of galaxy groups and clusters connected through the cosmic web's filamentary network. Understanding this structure reveals both the power of gravitational evolution to organize matter across vast scales and the limits cosmic expansion places on structure formation. The Sloan Great Wall's length of 1.4 billion light-years spans approximately 1.5% of the observable universe's diameter. This distance exceeds the size of many individual galaxy surveys, making detection possible only through large-scale mapping projects like the Sloan Digital Sky Survey, which obtained spectra for millions of galaxies across 1/3 of the sky. The structure's discovery required identifying that galaxies at redshifts between 0.073 and 0.083, corresponding to distances around 1 billion light-years, concentrate along a coherent wall-like formation rather than distributing randomly. This concentration is not overwhelming, but represents a 5 to 10 times enhancement over background galaxy density, sufficient to define a genuine structure rather than random statistical fluctuation. The wall's mass estimate approaches 10 to the 18th solar masses, roughly 1 quintillion solar masses or 1 million times the Milky Way's mass. This figure accounts for the thousands of galaxies visible along the structure plus associated dark matter required to explain gravitational effects and galaxy motions. The structure contains detectable clusters, including ones catalogued in the Abell cluster catalogue, along with numerous smaller groups and individual galaxies distributed throughout its volume. Total luminosity exceeds 10 to the 14th solar luminosities based on galaxy light measurements, though this represents only a fraction of total mass once dark matter is included. Mass-to-light ratios, around 100 solar units, are typical for large-scale structures where dark matter dominates visible matter by factors of 50 to 1. The Sloan Great Wall's location at redshift, approximately 0.08, places it roughly 1 billion light-years distant, meaning we observe it as it appeared 1 billion years ago when the universe was approximately 12.8 billion years old, 93% its current age. At this cosmic epoch, the universe had already reached substantial maturity, with the cosmic web's large-scale pattern fully developed. Observations reveal galaxy populations within the wall, similar to those in comparable structures at lower redshift, indicating that galaxy evolution had largely completed transforming primordial gas into stars, and that environmental processing had already shaped galaxy properties through billions of years of evolution. The wall's appearance demonstrates that cosmic structure on billion light-year scales existed when the universe was only 7% younger than today. Formation mechanisms for such enormous structures remain debated. Standard cosmological models predict that gravitational evolution can produce filamentary structures up to several hundred million light-years, but struggle to explain coherent formations approaching or exceeding 1 billion to light-years. The challenge is cosmological time. Only 13.8 billion years have elapsed since the Big Bang, during which expansion continuously works against gravitational collapse. Structures form through gravitational amplification of initial density fluctuations, but this process has finite speed determined by how fast matter can fall together. For billion light-year structures to assemble requires either that initial fluctuations on these scales were unusually large, or that we're observing chance alignments of smaller independent structures appearing connected in. Projection. The cosmic microwave background provides constraints on initial fluctuation amplitudes through its temperature variations. Observations by the Planck satellite show fluctuations of approximately 1 part in 100,000 on relevant angular scales, consistent with quantum fluctuations during cosmic inflation. Evolving these fluctuations forward through cosmic time using standard gravity and expansion produces structures matching observed filaments, walls, and voids on scales up to several hundred million light-years. Structures approaching 1 billion light-years represent 3 sigma or higher fluctuations, expected to be rare but not impossible. The Sloan Great Wall might represent one of these rare peaks in the cosmic density field, formed through standard processes but occurring infrequently across the observable universe. Alternatively, the Sloan Great Wall might represent a chance alignment of several independent filamentary structures appearing connected when viewed from Earth, but actually separated along our line of sight. This interpretation suggests that what appears as a single coherent billion light-year structure might actually be 3 or 4 smaller independent filaments spaced throughout the redshift range, 0.0732 to 0.083. From our vantage point, these separate structures align, creating the appearance of continuity. Testing this hypothesis requires detailed analysis of galaxy velocities within the structure, examining whether galaxies show coherent motions indicating physical connection, or whether velocity patterns fragment into independent components suggesting separate structures. Observational studies of the Sloan Great Wall examine its internal structure, searching for variations in galaxy density, clustering patterns, and velocity fields that might distinguish it from smaller, more typical structures. Surveys find that the wall contains multiple density peaks corresponding to galaxy clusters embedded within the overall structure, connected by lower density filaments, creating a network rather than uniform distribution. This hierarchical substructure is expected for genuine cosmic web formations, where matter concentrates at multiple scales, from individual galaxies to groups to clusters to the overall filament. The presence of this hierarchy supports interpreting the Sloan Great Wall as a coherent structure rather than chance alignment. The Sloan Great Wall's discovery motivated searches for even larger structures. Subsequent surveys identified additional candidates, including the huge, large quasar group spanning 4 billion light-years, though this structure's reality remains controversial. Claims of such enormous formations push or exceed the cosmological principle's homogeneity scale, raising questions about whether they represent genuine coherent structures or statistical artifacts. The debate continues as larger galaxy surveys, with improved redshift measurements, map cosmic structure with unprecedented detail. Each discovery tests our understanding of structure formation limits, refining models of how gravity organizes matter across the universe's largest observable scales. The Hercules Corona Borealis Great Wall testing cosmic limits. The Hercules Corona Borealis Great Wall represents perhaps the largest structure ever claimed in the observable universe, with estimates suggesting it spans approximately 10 billion light-years, though its existence and coherence remain controversial. Discovered in 2013 through analysis of gamma-ray burst distributions, this potential structure challenges fundamental assumptions about cosmic homogeneity and the maximum sizes structures can achieve through gravitational evolution. Located at redshifts between 1.6 and 2.1, corresponding to distances around 9 to 10 billion light-years, the structure appears as an overdensity of gamma-ray bursts that might trace an underlying galaxy distribution. Understanding whether this structure genuinely exists or represents statistical fluctuation tests of cosmological principles at their limits. Gamma-ray bursts, the most energetic explosions in the universe since the Big Bang, served as structure tracers in this discovery. These bursts originate from massive stellar core collapses or neutron star mergers, events that occur in galaxies. Mapping gamma-ray burst positions across the sky and determining their distances through redshift measurements creates a three-dimensional distribution that, in principle, traces galaxy locations. The discovery team, led by Lejos Balaz and colleagues, identified a concentration of gamma-ray bursts in the Hercules and Corona Borealis constellations at redshifts 1.6 to 2.1, spanning approximately 10 billion light-years if interpreted as a coherent structure. This concentration contained more bursts than expected from random distribution, suggesting an underlying overdensity of galaxies. The structure's claimed size of 10 billion light-years approaches the observable universe's radius of 46.5 billion light-years, representing roughly 20% of the maximum observable distance. This scale vastly exceeds the cosmological principle's homogeneity scale of approximately 300 million light-years, the distance beyond which the universe should appear statistically uniform in all directions. Structures exceeding the homogeneity scale challenge standard cosmology because insufficient time has elapsed since the Big Bang for gravitational evolution to organize matter coherently across such vast scales. The sound horizon at recombination, representing the maximum distance over which regions could have been in causal contact during the early universe, measures only about 1 billion light-years in today's coordinates. 10 billion light-year structures cannot have formed through processes requiring coordination across their entire volumes. Critics question whether the gamma-ray burst distribution genuinely represents a coherent structure or merely a statistical fluctuation. Gamma-ray bursts are rare events, with only hundreds detected at relevant redshifts available for analysis. Small number statistics make it difficult to distinguish genuine structure from random clustering. If 100 gamma-ray bursts distribute randomly across the sky, chance alone produces some apparent concentrations where more bursts cluster than average. Calculating whether observed clustering exceeds chance expectations requires careful statistical analysis accounting for selection effects, completeness variations across different sky regions, and the possibility of multiple independent tests, increasing the probability of finding spurious patterns somewhere. Alternative interpretations suggest the apparent structure might represent a chance superposition of several independent smaller structures aligned along our line of sight, rather than a single coherent 10 billion light-year formation. The redshift range 1.6 to 2.1 corresponds to a line of sight depth approaching 2 billion light-years in co-moving coordinates. Multiple filaments or walls spaced throughout this volume might appear connected when projected onto the sky, creating an illusion of continuity. Testing this requires galaxy redshift surveys in the same sky region, directly measuring galaxy distributions to determine whether they show coherent overdensity matching the gamma-ray burst pattern. Follow-up studies using galaxy surveys in the Hercules Corona Borealis region have yielded mixed results. Some analyses find galaxy overdensities consistent with the gamma-ray burst distribution, supporting the structure's existence. Others find no significant galaxy clustering or attribute observed patterns to known superclusters and filaments rather than a single coherent wall. The debate continues as additional data accumulates. Larger gamma-ray burst catalogues from missions like SWIFT and Fermi provide more events for statistical analysis. Deep galaxy surveys, including the Sloan Digital Sky Survey and successor programs, map galaxy distributions with improved completeness, testing whether galaxy density enhancements match gamma-ray burst clustering. The structure's reality has profound implications for cosmology. If genuine, it violates or stretches standard model predictions about maximum structure sizes. Possible explanations include that our understanding of structure formation is incomplete, that initial density fluctuations were larger on these scales than expected from inflation, or that some exotic process beyond standard gravity organized matter on 10 billion light-year scales. Each explanation requires revising aspects of current cosmology. Alternatively, if the structure is not real but represents statistical fluctuation or observer bias, this teaches important lessons about properly interpreting large-scale structure data and avoiding over-interpreting patterns in finite datasets. Theoretical work examines whether any known physics can produce 10 billion light-year structures. Standard cold dark matter cosmology, with observed cosmological parameters, struggles to explain such formations. The density fluctuations required to produce structures this large through gravitational amplification would need to be visible in cosmic microwave background observations, but CMB data shows no such large-scale fluctuations. This tension suggests either that the structure is not real, that it formed through non-standard processes, or that our models require modification. Alternative cosmological models, including modified gravity theories or non-standard inflation scenarios, might permit larger structures, but these models face constraints from other observations. The Hercules Corona Borealis Great Wall illustrates the challenges of studying the universe's largest scales. At 10 billion light-years, we observe regions as they appeared 10 billion years ago, when the universe was only 3.8 billion years old, less than 30% its current age. The young universe at those epochs was more compact, with higher matter density and faster structure formation. Yet, even accounting for this, explaining 10 billion light-year coherent structures remains challenging. Whether real or not, claims of such enormous formations push observational cosmology to its limits, testing both measurement techniques and theoretical understanding of how the universe organizes matter across the largest observable scales. Laniakea, our home supercluster, defined by motion. Laniakea supercluster represents a revolutionary understanding of cosmic structure, defined not by static galaxy density, but by dynamic velocity flows, revealing how galaxies move under gravitational influence. Spanning approximately 520 million light-years and containing roughly 100,000 galaxies with total mass around 10 to the 17th solar masses, Laniakea encompasses the local group, Virgo cluster, and numerous other galaxy groups and clusters, all flowing toward a common gravitational center. The name Laniakea, chosen from Hawaiian meaning immeasurable heaven, appropriately captures this enormous structure's scale while honoring the Discovery team's connections to Hawaii, where much of the crucial data originated. Understanding Laniakea fundamentally changed our cosmic address, revealing that our galactic neighborhood extends far beyond previous estimates. The traditional Virgo supercluster, defined in the mid-20th century through galaxy density measurements, encompassed approximately 110 million light-years centered on the Virgo cluster, with the local group positioned on the outskirts. This structure contained approximately 100,000 galaxies, with total mass around 10 to the 15th solar masses, representing our cosmic neighborhood as understood for decades. However, 2014 analysis by Brent Tully, Hélène Courtois, Yehuda Hoffman, and Daniel Pomered revealed this definition was incomplete. Using peculiar velocity measurements for thousands of galaxies, velocities corrected for cosmic expansion's smooth Hubble flow, the team mapped actual galaxy motions caused by gravitational attraction rather than expansion. Velocity flow analysis identifies basins of attraction analogous to watersheds on Earth, where water flows downhill toward common drainage points. In space, galaxies flow along gravitational gradients toward mass concentrations, creating basins where all matter within a region shares a common destiny. Mapping these basins required measuring distances and velocities for galaxies across hundreds of millions of light-years, a monumental observational effort. The team combined data from multiple sources, including the Cosmic Flows 2 catalog containing distance measurements for 8,000 galaxies, revealing that the local group, Virgo cluster, Great Attractor region, and numerous other structures all belong to a single velocity flow basin extending 520 million light-years. Laniakea's boundaries are defined by velocity flow separatrices, surfaces where flow directions diverge, marking transitions between different attraction basins. These boundaries are not physical walls, but mathematical surfaces in velocity space, separating regions, flowing toward different attractors. Within Laniakea, all galaxies flow toward the structure's center of mass, located near the Great Attractor region, in the direction of Norma and Centaurus clusters. Approximately 250 million light-years from the local group, flow velocities reach 600 to 700 kilometers per second for galaxies deep within the structure, though velocities decrease toward boundaries where competing attractions from neighboring superclusters like Perseus Pisces and Shapley become comparable to Laniakea's pull. The structure extends from the Perseus-Pisces supercluster boundary on one side, through the Virgo cluster, to the Great Attractor region near Norma and Centaurus clusters, encompassing multiple previously identified superclusters, including the traditional Virgo supercluster, Hydra Centaurus supercluster, Pavo Indus supercluster, and portions of the Centaurus supercluster. These smaller structures, defined by local density enhancements, represent substructures within the larger velocity-defined basin. The Virgo cluster, despite its proximity at 54 million light-years and historical prominence, contains only approximately 1% of Laniakea's total mass. Most mass concentrates in more distant regions toward the Great Attractor and Shapley concentration. The Great Attractor itself represents a gravitational anomaly drawing the local group and surrounding structures at several hundred kilometers per second. Located approximately 200 million light-years away behind the Milky Way's disk where dust obscures optical observations, the Great Attractor remained mysterious for decades. Infrared and radio observations penetrating this dust revealed multiple massive galaxy clusters, including the Norma cluster, though total observed mass falls short of explaining measured velocities. Some models suggest the Shapley concentration at 650 million light-years, technically outside Laniakea's boundaries, contributes significantly to observed motions, with our peculiar velocity representing combined influence of both Great Attractor and more distant Shapley pulling from beyond Laniakea. The local group resides on Laniakea's outskirts, in a relatively underdense region, flowing toward the center at velocities exceeding 600 km per second when all velocity components are combined. This motion results from gravitational attractions of Virgo cluster, pulling at 200 to 300 km per second. The Great Attractor contributing another 200 to 300 km per second, and more distant masses adding their influence. This peculiar velocity was recognized decades ago through observations showing our velocity relative to the cosmic microwave background. Rest frame is 630 km per second toward Hydra Centaurus direction. But identifying specific mass concentrations causing this motion required mapping galaxy distributions and velocities across hundreds of millions of light-years. Laniakea's discovery transformed understanding of cosmic structure by demonstrating that velocity-based definitions reveal coherent structures invisible to density-based methods. Traditional supercluster definitions identified local density enhancements, but missed broader gravitational connections. Velocity flow methods trace gravitational influence directly, revealing how matter actually moves and which structures are dynamically connected versus merely appearing close in projection. This approach has been applied to map the cosmic web on larger scales, identifying dozens of superclusters like Laniakea throughout the nearby universe within 1 billion light-years. Each supercluster represents a basin of attraction where hundreds of thousands of galaxies flow toward common centers, creating the universe's largest gravitationally connected or semi-connected structures. The name Laniakea, suggested by Nawar R. Napoleon, Associate Professor of Hawaiian Language at Kapiolani Community College, acknowledges the discovery team's connection to Hawaii, where much peculiar velocity data came from observations at telescopes, including those on Mauna Kea. The Hawaiian name appropriately captures the structure's immensity, immeasurable or immense heaven, reflecting both its vast scale and the sense of wonder it inspires. The discovery paper, published in Nature in September 2014, provided the first clear picture of our home supercluster's extent and dynamics, answering questions about local, large-scale structure that had puzzled astronomers for decades. Subsequent work has refined Laniakea's boundaries, identified neighboring superclusters, and mapped velocity flows throughout the nearby universe, revealing the cosmic web's detailed structure and our place within it, the Great Attractor pulling our cosmic neighborhood. The Great Attractor represents one of astronomy's most intriguing mysteries, a gravitational anomaly pulling the local group, Virgo cluster, and surrounding structures at hundreds of kilometers per second toward a region hidden behind the Milky Way's galactic plane. Located approximately 220 million light-years away in the direction of Triangulum, Australis, Norma, and Centaurus constellations, this overdensity was inferred from galaxy motions decades before direct observations revealed its nature. The Great Attractor's position in the zone of avoidance, where Milky Way dust obscures optical observations, created observational challenges requiring infrared and radio observations to penetrate obscuring material. Understanding this structure reveals how mass concentrations shape large-scale galaxy flows and demonstrates how gravitational effects can be detected even when objects themselves remain partially hidden. Discovery of the Great Attractor emerged from studies measuring galaxy peculiar velocities throughout the 1970s and 1980s. Astronomers, including Sandra Faber, Donald Lynden Bell, and colleagues measured distances and redshifts for galaxies across the sky, comparing observed velocities to predictions from smooth cosmic expansion. They found that the local group and hundreds of surrounding galaxies within approximately 100 million light-years show coherent motion at approximately 600 kilometers per second toward a specific sky direction near Hydra and Centaurus constellations. This large-scale flow, dubbed the Great Attractor Flow, indicated enormous mass concentrations beyond the Virgo cluster, pulling matter gravitationally despite being located behind the Milky Way's obscuring disk. Calculating the mass required to produce observed velocities yielded estimates around 10 to the 16th solar masses within approximately 160 million light-years of the assumed center. This mass exceeds the Virgo cluster by roughly 100 times, suggesting a concentration containing multiple massive galaxy clusters rather than a single structure. The challenge became identifying this mass observationally when the critical region lay behind the zone of avoidance, where dust extinction at optical wavelengths exceeds 10 magnitudes in the densest regions, reducing apparent brightness by factors of 10,000 and completely obscuring background galaxies from visual observation. Infrared surveys at 2 to 10 micron wavelengths penetrate much of this dust, revealing previously unknown galaxies in the Great Attractor region. The 2-micron all-sky survey, mapping the entire sky at near-infrared wavelengths, identified thousands of galaxies behind the zone of avoidance, including major clusters. The Norma cluster emerged as one of the richest clusters in the Great Attractor region, located approximately 200 million light-years away, containing over 1,000 galaxies within 10 million light-years. X-ray observations from satellites, including Rosat and Chandra, revealed hot intra-cluster gas emitting X-rays, indicating total mass approaching 10 to the 15th solar masses for Norma alone, comparable to the Virgo cluster. Additional clusters discovered in the region include the Centaurus cluster at approximately 170 million light-years, a Bell 3,627 forming part of the Norma complex, and several other significant concentrations. Summing visible mass from these clusters yields several times 10 to the 15th solar masses, substantial but still potentially insufficient to fully explain the 600 km per second peculiar velocities measured across large volumes. This mass deficit suggests either that significant mass remains undetected behind residual dust obscuration, or that more distant structures beyond the Great Attractor region contribute substantially to observed motions. The Shapley concentration at 650 million light-years, well beyond the Great Attractor's nominal position, represents the largest known mass concentration in the nearby universe, with total mass potentially exceeding 10 to the 17th solar masses. Discovered by Harlow Shapley in the 1930s, this enormous supercluster contains over 25 rich galaxy clusters concentrated within approximately 100 million light-years. Recent analyses suggest the Shapley concentration exerts gravitational influence across hundreds of millions of light-years, potentially contributing significantly to the local group's peculiar velocity alongside or even dominating the Great Attractor's influence. This interpretation suggests the Great Attractor region represents an intermediate concentration between the local group and the more distant, more massive Shapley pulling from beyond. Velocity field mapping throughout the Laniakea supercluster reveals complex flows combining multiple mass concentrations influences. The local group flows toward Virgo at 200 to 300 km per second, while simultaneously flowing toward the Great Attractor region at comparable velocity. These motions combine with additional components toward the Shapley concentration, creating the observed 630 km per second peculiar velocity relative to cosmic microwave background. Disentangling individual contributions requires modeling mass distributions and calculating expected gravitational effects. Comparing predictions to observed velocity fields across thousands of galaxies spanning hundreds of millions of light-years. The Great Attractor's name, while evocative, might be somewhat misleading if Shapley dominates our motion. Some researchers prefer terms like Great Attractor Complex or Norma Centaurus Complex to emphasize the region's true nature as a collection of multiple clusters rather than a single object. Regardless of terminology, the region clearly represents a significant mass concentration pulling the local group and surrounding structures, shaping large-scale flows within Laniakea. Understanding its precise mass distribution and relationship to the Shapley concentration remains active research, requiring continued observations penetrating the zone of avoidance and refined modeling of gravitational dynamics across hundreds of millions of light-years. The Great Attractor mystery illustrates challenges of studying regions obscured by our galaxy's disk and the power of inferring structure through gravitational effects, even when direct observation proves difficult. The story demonstrates how astronomy combines multiple techniques, from velocity measurements, revealing hidden mass, to infrared observations penetrating dust, to X-ray imaging detecting hot gas, gradually unveiling structures that optical telescopes cannot observe. The Great Attractor remains partially mysterious despite decades of study, reminding us that even in our cosmic neighborhood within a few 100 million light-years, significant structures can evade complete characterization. As observations improve and models become more sophisticated, our understanding of this region and its role in shaping local large-scale structure will continue to evolve. The Shapley concentration, the most massive nearby structure, the Shapley concentration stands as the most massive structure within 1 billion light-years, containing over 25 rich galaxy clusters, with combined mass potentially exceeding 10 to the 17th solar masses, concentrated within approximately 100 million light-years. Located 650 million light-years away in the constellation Centaurus, this enormous supercluster was discovered by Harlow Shapley in the 1930s during photographic surveys mapping galaxy distributions across the sky. Shapley recognized an unusual concentration of galaxies and clusters in this region, but lacked the technology to measure distances accurately. Modern observations reveal the full extent of this structure, showing it ranks among the universe's most significant mass concentrations and exerts gravitational influence across hundreds of millions of light-years, potentially affecting our local group's motion through space. The Shapley concentration contains multiple Abell clusters, rich galaxy clusters catalogued by George Abel in 1958 through systematic photographic surveys. Major members include Abel 3558, the concentration's dominant cluster containing over 200 bright galaxies, Abel 3562, located nearby, forming a close pair with A 3558, and Abel 3571, among several others, distributed throughout the 100 million light-year volume. Each cluster individually contains masses comparable to the Virgo cluster, approximately 1 to 2 times 10 to the 15th solar masses, but their proximity creates a combined gravitational potential well far exceeding any individual member. The clusters are not randomly scattered, but show signs of ongoing dynamical interactions, with some pairs approaching each other at velocities exceeding 1,000 kilometers per second. X-ray observations from satellites including ROSAT, Chandra, and XMM Newton reveal enormous quantities of hot gas at temperatures 10 to 100 million Kelvin, filling space between clusters. This intracluster and supercluster gas emits X-rays through thermal Bremsstrahlung radiation, allowing mass measurements through gas temperature and density profiles. The observations indicate that gas mass exceeds all cluster galaxies combined, with total baryonic matter reaching several times 10 to the 14th solar masses. Including dark matter inferred from gravitational effects raises total mass estimates to 10 to the 17th solar masses, or potentially higher, making Shapley roughly 100 times more massive than the traditional Virgo supercluster definition and comparable to Laniakea's total mass. The structure's gravitational influence extends far beyond its visible boundaries. Galaxies within 300 million light-years of Shapley's center show coherent motions of several hundred kilometers per second directed toward the concentration, indicating that Shapley's gravity affects dynamics across volumes spanning significant fractions of the observable universe's radius. Some studies suggest the local group's peculiar velocity relative to cosmic microwave background has significant component toward Shapley, beyond contributions from Virgo cluster and Great Attractor, implying Shapley might dominate our motion despite being 650 million light-years distant. This interpretation remains debated, with different analyses attributing varying fractions of our peculiar velocity to different mass concentrations. Shapley's location at 650 million light-years corresponds to redshift approximately 0.046, meaning we observe it as it appeared 650 million years ago when the universe was approximately 13.15 billion years old, roughly 95% its current age. At this relatively recent epoch, cosmic structure had reached substantial maturity, with the cosmic web fully developed and most galaxy evolution already completed. The Shapley concentration's appearance demonstrates that extremely massive structures existed when the universe was only 5% younger than today, having assembled through billions of years of gravitational evolution from initial density fluctuations present in the cosmic microwave background. Formation history of such massive concentrations requires special initial conditions. Standard cosmological models predict that structures form hierarchically, with small objects forming first, then merging into progressively larger systems. The most massive structures represent rare peaks in the cosmic density field, several sigma fluctuations that occur infrequently across large volumes. Shapley likely formed from a region that was slightly overdense in the early universe by margins of perhaps 10 to 20% above cosmic average. This modest initial overdensity amplified through billions of years of gravitational evolution, attracting surrounding matter and growing into the enormous concentration observed today. Computer simulations of cosmic structure formation occasionally produce Shapley-like concentrations when evolved from initial conditions matching cosmic microwave background observations. These simulations show that massive superclusters form at intersections of multiple large-scale filaments, locations where matter flows converge from many directions. The simulated structures match observed properties including total mass, cluster count, spatial extent, and velocity fields, confirming that standard gravitational physics can produce Shapley-like formations through natural evolution. However, such massive concentrations are rare in simulations, typically occurring only once or a few times within volumes comparable to the observable universe, consistent with Shapley representing an extreme but not impossible fluctuation. The Shapley concentration serves as a cosmological laboratory testing structure, formation theories, and dark energy effects. Its mass and distance make it sensitive to cosmological parameters, including matter density, dark energy properties, and the spectrum of primordial fluctuations. Different cosmological models predict different abundances of extremely massive structures at various redshifts. Observations constraining how many Shapley-like concentrations exist at different cosmic epochs test whether models correctly describe structure growth from early universe to present. Current observations suggest that massive superclusters like Shapley are rare but not impossibly so given standard lambda CDM cosmology with observed parameters. Future observations will continue refining Shapley's properties and testing its role in shaping local, large-scale dynamics. The Euclid Space Telescope, launched in 2023, will map galaxy distributions across billions of light-years with unprecedented precision, identifying additional massive concentrations and constraining their abundance evolution. Ground-based surveys, including the Vera Rubin Observatory's Legacy Survey of Space and Time, will obtain spectra for tens of millions of galaxies, measuring distances and velocities that map velocity flows around Shapley and other major concentrations. These observations will determine whether Shapley truly represents the dominant mass concentration within 1 billion light-years, or whether even larger structures exist at greater distances, hidden by current survey limitations. The Shapley concentration illustrates that the universe contains structure on all scales, from individual galaxies through clusters and superclusters to the cosmic web's largest elements. Understanding such massive concentrations reveals how gravity organizes matter across hundreds of millions of light-years, approaching scales where cosmic expansion and dark energy begin competing effectively with gravitational attraction. Shapley represents one of the largest gravitationally significant structures within the observable universe, a concentration so massive that its influence extends across significant cosmic volumes, potentially affecting the motion of our local group, despite being separated by over 500 million light-years of expanding space. Dark matter, the invisible scaffolding of structure. Dark matter comprises approximately 85% of all matter in the universe, yet it remains invisible, detectable only through gravitational effects on visible matter and light. This mysterious substance forms the scaffolding upon which all cosmic structure builds, providing the gravitational potential wells within which galaxies form and the filamentary framework creating the cosmic web's architecture. Understanding dark matter's role in structure formation reveals why the universe organizes into the patterns we observe, rather than distributing matter uniformly or concentrating it entirely into isolated clumps. Without dark matter, cosmic structure as we know it could not exist. Galaxies would not have formed during the available time. The cosmic web's filaments would not persist, and the universe would appear fundamentally different from observations. Evidence for dark matter emerged from multiple independent observations beginning in the 1930s. Fritz Zwicky studied the Coma cluster, measuring galaxy velocities through Doppler shifts and finding that galaxies moved so fast that visible matter alone could not bind the cluster gravitationally. Velocities reaching thousands of kilometers per second required far more mass than stars and gas provided. Zwicky proposed that unseen dark matter supplied additional gravity, a hypothesis that seemed radical but gradually gained acceptance. In the 1970s, Vera Rubin and colleagues measured rotation curves for spiral galaxies, plotting how fast stars orbit at different distances from galactic centers. They found that rotation velocities remain constant far from galactic cores, rather than declining as expected if only visible matter existed. This flat rotation curve pattern, observed in galaxy after galaxy, requires dark matter halos extending well beyond visible disks. Gravitational lensing provides perhaps the most direct dark matter evidence. When massive objects like galaxy clusters lie between Earth and more distant sources, their gravity bends light from background objects, creating distorted or multiple images. The lensing strength directly measures total mass, including dark matter. Observations show that cluster lensing masses exceed visible matter by factors of 50 to 100, confirming that most mass is invisible. The Bullet cluster, officially designated 1E0657-56, offers particularly compelling evidence. This system resulted from a collision between two galaxy clusters about 150 million years ago. During the collision, galaxies passed through each other, mostly unaffected since galaxies are mostly empty space. However, hot X-ray emitting gas in each cluster collided and was slowed by electromagnetic interactions, creating shock waves visible in X-ray images. Gravitational lensing maps show that most mass is not where the gas accumulated, but where galaxies are, demonstrating that most matter is dark, collisionless, and concentrated with galaxies rather than gas. Dark matter's nature remains one of physics' greatest mysteries. Leading candidates include WIMPs, weakly interacting massive particles with masses ranging from a few to thousands of proton masses, interacting only through gravity and the weak nuclear force. If WIMPs exist with appropriate properties, they would have been produced in the early universe's hot, dense conditions, and their abundance today would match observed dark matter density. Direct detection experiments search for rare WIMP collisions with atomic nuclei using detectors deep underground to shield from cosmic rays. Despite decades of searching with increasingly sensitive experiments, no confirmed WIMP detections exist, constraining their properties or suggesting they are not the answer. Alternative candidates include axions, hypothetical particles with extremely low mass, around 10 to the minus fifth electron volts or lighter, billions of times lighter than electrons. Axions were originally proposed to solve the strong CP problem in quantum chromodynamics. If they exist, enormous numbers would be needed to comprise dark matter, perhaps 10 to the 85th axions in the observable universe. Axion detection experiments use strong magnetic fields to convert axions into photons, searching for these signals but have not yet found confirmed detections. Sterile neutrinos, hypothetical neutrinos interacting only through gravity, represent another candidate with masses potentially ranging from electron volts to kiloelectron volts. Some X-ray observations hint at potential sterile neutrino decay signals, but evidence remains inconclusive. Dark matter's role in structure formation becomes clear through computer simulations. Starting from initial density fluctuations observed in the cosmic microwave background, simulations evolve dark matter forward through cosmic time using only gravity. The simulations show dark matter collapsing into halos, ranging from galaxy mass halos at millions to billions of solar masses, to cluster mass halos exceeding 10 to the 14th solar masses. These halos connect through filaments of diffuse dark matter, creating the cosmic web's structure. Ordinary baryonic matter, following dark matter's gravitational potential wells, accumulates where dark matter concentrated, forming galaxies where halos became sufficiently massive. The visible cosmic web traces underlying dark matter distribution, making galaxy surveys powerful tools for mapping the universe's dominant component. The cold dark matter paradigm, where dark matter particles move slowly compared to light speed, successfully reproduces observed large-scale structure. Simulations using cold dark matter produce filaments, walls, clusters, and voids matching galaxy survey observations. The power spectrum, describing structure, amplitude versus scale, matches measurements from galaxy clustering. Cluster abundances at different redshifts match observations. The cosmic web's detailed topology matches observed patterns. This success confirms that cold dark matter correctly describes structure formation on scales from tens of thousands to hundreds of millions of light years. However, cold dark matter faces potential challenges on smaller scales, including the missing satellites problem, where simulations predict more low-mass halos than observed dwarf galaxies, and the core cusp problem, where simulations produce cuspy central density profiles, while observations suggest flatter cores. Dark matter's distribution determines where galaxies form and how they evolve. High-density peaks in the dark matter field become galaxy clusters, locations where multiple halos merge, creating deep potential wells that attract and bind thousands of galaxies. Moderate density regions form galaxy groups with a few large halos. Filamentary regions contain chains of smaller halos where individual galaxies and small groups form. Void regions have few halos and correspondingly few galaxies. This hierarchy means that galaxy properties reflect their dark matter environment. Galaxies in massive halos undergo different evolution than those in small halos, experiencing different merger rates, gas accretion rates, and environmental effects. Understanding dark matter distribution is essential for understanding galaxy formation and evolution across cosmic history. Future observations will continue constraining dark matter properties through its gravitational effects on cosmic structure. Large-scale surveys like Euclid and the Vera Rubin Observatory will map dark matter distribution through gravitational lensing across billions of light years, measuring how dark matter clustering evolves with cosmic time. These measurements test whether dark matter behaves as expected from cold dark matter models or shows deviations indicating warm dark matter, self-interacting dark matter, or other variants. Direct detection experiments continue searching for dark matter particles, with next-generation detectors achieving sensitivities orders of magnitude better than current experiments. If dark matter consists of particles interacting even weakly with ordinary matter, eventually these experiments should detect them, revealing dark matter's fundamental nature and explaining the substance-forming cosmic structures in visible scaffolding. Simulating the cosmos, how computers reveal structure. Computer simulations have revolutionized our understanding of cosmic structure formation, allowing astronomers to evolve the universe forward from initial conditions, billions of years, in a matter of hours or days of computation. These simulations solve gravitational equations for millions or billions of particles representing dark matter and gas, tracking how matter collapses into halos, forms filaments, and creates the cosmic web over billions of years of cosmic time. The resulting virtual universes match observed structure with remarkable accuracy, reproducing galaxy clustering patterns, filament morphologies, void properties, and cluster abundances. Understanding how simulations work and what they reveal demonstrates the power of combining observational data with theoretical modeling to comprehend how simple physical laws operating over vast timescales produce the complex structures we observe today. The Millennium Simulation, conducted in 2005 by an international team led by Volker Springel, exemplified the state-of-the-art for its era. This calculation followed over 10 billion dark matter particles in a cubic volume measuring 500 million light-years on a side, spanning from early universe at redshift 127, when the universe was only 12 million years old, to present day. The simulation required over 1 month of continuous calculation using 512 processors on a supercomputer at the Max Planck Institute. The resulting data exceeded 25 terabytes, capturing how dark matter particles moved under mutual gravitational attraction, collapsing into halos and creating cosmic web structure. Post-processing algorithms identified dark matter halos, tracked their merger histories, and populated them with galaxies using semi-analytic models relating halo properties to galaxy formation. Initial conditions for simulations come from cosmic microwave background observations. The Planck satellite measured temperature fluctuations across the entire sky with unprecedented precision, revealing density variations of approximately 1 part in 100,000 at redshift 1090, when the universe was 380,000 years old. These fluctuations represent the seeds of all future structure, imprinted during cosmic inflation in the universe's first moments. Simulations convert these observed fluctuation patterns into particle distributions, matching the same statistical properties, then evolve forward using gravity and expansion. The fact that simulations starting from CMB, initial conditions, reproduce observed present-day structure confirms our understanding of how structure grows from tiny early fluctuations to prominent modern cosmic web. Gravitational evolution in simulations operates through n-body techniques, solving Newton's law or Einstein's general relativity for systems containing millions to billions of particles. Each particle represents a mass element, typically millions to billions of solar masses in dark matter. The simulation calculates gravitational forces between all particles, updates velocities and positions according to these forces, then repeats the process for billions of time steps spanning cosmic history. This conceptually simple procedure requires sophisticated numerical methods to achieve accuracy and efficiency. Direct calculation of all particle pair interactions scales as n squared, becoming prohibitively expensive for large n. Modern simulations use hierarchical tree methods or particle mesh techniques, reducing computational cost to n times log n, enabling calculations with billions of particles. Gas dynamics adds complexity beyond pure dark matter simulations. Gas interacts through hydrodynamic forces in addition to gravity, requiring solving fluid equations for pressure, temperature, and density alongside gravitational equations. Gas can shock, heat, cool, and form stars, processes that affect structure formation. Early simulations use smoothed particle hydrodynamics, representing gas as particles that interact through prescribed force laws, mimicking fluid behavior. Modern simulations increasingly use adaptive mesh techniques, dividing space into cells and solving hydrodynamic equations on grids that refine automatically in dense regions. These methods better capture shocks, turbulence, and other fluid phenomena essential for realistic galaxy formation. Subgrid physics represents processes occurring below simulation resolution. Even the highest resolution simulations cannot directly resolve individual stars, supernova explosions, or black hole accretion, phenomena occurring on scales of light years or smaller, while simulation resolution is thousands of light years. Instead, simulations incorporate these effects through subgrid models, prescriptions that approximate aggregate effects based on local conditions. Star formation is modeled by converting gas to stars when density and temperature cross thresholds. Supernova feedback is modeled by injecting energy into surrounding gas. Black hole growth and AGN feedback are modeled by accreting gas onto black hole particles and returning energy to surroundings. These subgrid models introduce uncertainties, as exact prescriptions are uncertain and different choices produce different outcomes. The Illustris and Illustris TNG simulations demonstrate modern capabilities. Illustris TNG, completed in 2018, evolved over 10 billion particles, including both dark matter and gas, in a 300 million light-year cube, with resolution reaching 1,000 light-years in dense regions. The simulation tracked cosmic evolution from redshift 127 to present, incorporating star formation, stellar evolution, supernova feedback, black hole growth, AGN feedback, magnetic fields, and chemical enrichment. The resulting virtual universe contains millions of resolved galaxies with properties including masses, sizes, colors, and morphologies comparable to observations. Comparing simulated and observed galaxies tests whether implemented physics correctly describes galaxy formation, revealing which processes are essential and which require refinement. Simulations reveal how cosmic structure evolved through time. At high redshift corresponding to early universe, simulations show mostly small dark matter halos forming from initial fluctuations, containing proto-galaxies just beginning star formation. By intermediate redshift around 2, corresponding to cosmic time when the universe was 3 to 4 billion years old, the cosmic web has emerged with filaments, connecting clusters. Though structures are smaller and less massive than today, by present day, simulations show the mature cosmic web with prominent filaments, massive clusters, and large voids matching observations. This evolutionary sequence demonstrates that structure grows hierarchically, with small objects merging to build larger systems over billions of years. Predictions from simulations guide observational programs. Simulations predict how many galaxy clusters should exist at different masses and redshifts, testable through cluster surveys. They predict galaxy clustering strength versus scale, testable through galaxy surveys. They predict how voids evolve, testable through void catalogues. When predictions match observations, this confirms simulation physics. When mismatches occur, this identifies where understanding is incomplete, motivating theoretical work and additional observations. This interplay between simulation and observation drives progress in understanding cosmic structure formation. Future simulations will push to larger volumes and higher resolutions simultaneously. Exascale supercomputers coming online in the mid-2020s will enable simulations with hundreds of billions of particles in cosmological volumes, resolving galaxy formation while capturing large-scale structure across billions of light-years. These simulations will test whether small-scale galaxy formation physics remains consistent with large-scale structure constraints, potentially revealing new physics if discrepancies emerge. Machine learning techniques are being applied to accelerate simulations and improve subgrid models, learning optimal prescriptions from data rather than relying on theoretical guesses. The combination of improved computing power, better numerical methods and machine learning will produce virtual universes of unprecedented realism, transforming simulations from qualitative tools to precision instruments quantitatively matching observations. From quantum fluctuations to cosmic web, the origin of structure. All cosmic structure, from individual galaxies to the largest filaments and walls, originated from quantum fluctuations during cosmic inflation in the universe's first moments. These microscopic random variations in energy density generated by quantum uncertainty during an exponential expansion phase, lasting perhaps 10 to the minus 35 to 10 to the minus 32 seconds after the Big Bang, were stretched to astronomical scales by inflation's rapid expansion. When inflation ended, these fluctuations remained imprinted on matter and radiation as tiny density variations, approximately 1 part in 100,000 deviations from perfect uniformity. Over billions of years, gravitational amplification transformed these subtle variations into the dramatic structures we observe today. Understanding this journey from quantum to cosmic scales reveals one of nature's most remarkable processes: how the smallest phenomena in physics seed the largest structures in the universe. Cosmic inflation, proposed in the 1980s by Alan Guth and others, solves several cosmological puzzles while simultaneously explaining structure's origin. Inflation posits that the universe underwent exponential expansion driven by a scalar field called the inflaton in the first fraction of a second after the Big Bang. During inflation, the universe expanded by factors exceeding 10 to the 26, smoothing initial irregularities and explaining why the universe appears so uniform on large scales. However, inflation could not eliminate quantum fluctuations. The Heisenberg uncertainty principle ensures that quantum fields fluctuate randomly, creating temporary energy density variations. During inflation, these quantum fluctuations were stretched from subatomic scales to cosmological scales by the exponential expansion, becoming classical density perturbations frozen into the universe's structure. The fluctuation spectrum produced by inflation has specific properties testable through observations. Quantum fluctuations during inflation create nearly scale-invariant perturbations, meaning fluctuation amplitude varies slowly with scale rather than strongly preferring certain sizes. The spectral index measuring this scale dependence is approximately 0.96, slightly below perfect scale invariance. This prediction matches cosmic microwave background observations precisely, providing strong evidence that observed fluctuations indeed originated from quantum processes during inflation. The fluctuations are also Gaussian, meaning their statistical distribution follows a bell curve with no preferred phases or correlations beyond those expected from random processes. Again, observations confirm this prediction, supporting the inflationary origin of structure. Density fluctuations at recombination. When the universe was 380,000 years old and the cosmic microwave background formed, had amplitudes around 1 part in 100,000. The cosmic microwave background's temperature variations directly measure these fluctuations, showing hot spots where density was slightly higher and cold spots where density was slightly lower. The fluctuation's angular scale distribution, quantified through the CMB power spectrum, reveals detailed information about cosmic composition, geometry, and the fluctuation's initial properties. Observations match predictions from inflation-generated quantum fluctuations evolved through recombination, confirming the theoretical framework connecting quantum physics to cosmic structure. After recombination, density fluctuations grew through gravitational instability. Regions slightly denser than average possessed slightly stronger gravity, attracting surrounding matter and becoming denser. This positive feedback amplified initial tiny fluctuations into significant overdensities over billions of years. Dark matter dominated this process because, unlike baryonic matter, dark matter does not interact electromagnetically and thus avoids pressure support that resists gravitational collapse. Dark matter overdensities collapsed freely under self-gravity, forming halos that then attracted baryonic matter. The first dark matter halos formed when the universe was approximately 100 million years old, providing sites where the first stars and galaxies would later form. Structure formation proceeded hierarchically, with small structures forming first, then merging into larger systems. This bottom-up scenario follows naturally from the properties of cold dark matter and the fluctuation spectrum. Small-scale fluctuations entered the horizon earlier, meaning they had more time to grow through gravitational amplification. Large-scale fluctuations entered the horizon later and grew more slowly. The first objects forming were small halos, with masses around 1 million solar masses, possibly hosting the first stars. These halos merged to form larger halos, hosting the first galaxies. Continued merging built galaxy groups, then clusters, then superclusters, creating hierarchical structure from small to large scales over billions of years. Linear growth during the radiation-dominated and early matter-dominated epochs proceeded slowly, with overdensity amplitudes growing proportional to the scale factor in matter domination and remaining constant during radiation domination. Once overdensities reached amplitudes around unity, where overdense regions are roughly twice average density, linear theory breaks down and nonlinear collapse begins. During nonlinear collapse, overdense regions stop expanding, with cosmic flow reach maximum size, then collapse under self-gravity, virializing into stable structures. The transition from linear to nonlinear occurred first on small scales, where fluctuations had larger initial amplitudes, then progressively on larger scales as those fluctuations grew. This created the observed pattern where small structures like galaxies are highly nonlinear and virialized, while the largest structures, like superclusters, remain partially linear, still in the process of collapse. The cosmic web's pattern emerged naturally from gravitational collapse's three-dimensional nature. Overdense regions typically have elongated or sheet-like shapes rather than spherical symmetry. Collapse proceeds fastest along the shortest axis where gravitational pull is strongest, creating pancake-like structures. Continued collapse along the next axis transforms pancakes into filaments. Finally, collapse along the third axis creates nodes where galaxy clusters form. This explains why the cosmic web exhibits one-dimensional filaments, two-dimensional walls, and three-dimensional nodes rather than uniform structure. The pattern reflects how gravity organizes matter in 3 dimensions, creating the foam-like architecture visible in galaxy surveys. Dark energy's emergence, approximately 5 billion years ago, affected structure growth by accelerating cosmic expansion. Before dark energy dominated, matter's gravity slowed expansion, allowing structures to continue growing through gravitational attraction, overcoming cosmic expansion. Once dark energy dominated, accelerated expansion works against gravitational collapse on large scales, slowing or halting growth of structures larger than galaxy clusters. Clusters already formed remain bound because internal gravity exceeds dark energy's repulsive effect. But larger structures like superclusters cannot collapse, and new large-scale structure formation effectively ceased. The cosmic web we observe today represents the endpoint of structure growth, with future evolution consisting mainly of existing structures merging rather than new large structures forming. Understanding structure's origin from quantum fluctuations to cosmic web represents one of cosmology's greatest achievements, connecting fundamental physics at smallest scales to observable structure at largest scales. The story demonstrates how simple physical laws, operating over vast timescales, transform subtle initial conditions into complex patterns. It shows how observations across scales from CMB to galaxy surveys all fit together into a coherent picture of cosmic evolution. And it reveals that the universe's largest structures trace their ancestry to quantum uncertainty in the first moments after the Big Bang, demonstrating the profound connections between quantum mechanics, general relativity, and cosmology in shaping the universe we observe today. Measuring cosmic structure, the tools of discovery. Understanding cosmic structure requires measuring distances, positions, and motions for millions of galaxies across billions of light years, a monumental observational task that has occupied astronomers for decades. The tools for this work include ground-based telescopes obtaining spectra to measure redshifts and distances, space telescopes imaging galaxies with unprecedented clarity, gravitational lensing revealing dark matter distributions, and increasingly sophisticated analysis techniques extracting maximum information from observations. These measurements build three-dimensional maps showing how galaxies cluster, revealing filaments, walls, voids, and superclusters that comprise the cosmic web. Understanding the techniques that made these discoveries possible demonstrates how modern astronomy combines advanced technology with theoretical understanding to map the universe's largest structures. Redshift surveys represent the primary tool for mapping cosmic structure. A galaxy's spectrum contains absorption and emission lines at specific wavelengths determined by the elements present. When galaxies move away due to cosmic expansion, these wavelengths stretch proportionally, a phenomenon called redshift. Measuring the redshift provides distance through Hubble's law. Recession, velocity, equals the Hubble constant times distance. Converting velocity to distance requires knowing the Hubble constant, currently measured at approximately 70 km per second per megaparsec. For nearby galaxies, uncertainties in the Hubble constant significantly affect distance estimates. For distant galaxies, where cosmic expansion dominates peculiar velocities, redshift reliably indicates distance. The Sloan Digital Sky Survey exemplifies modern redshift survey capabilities. Operating from 2000 through 2020, SDSS obtained spectra for over 4 million galaxies across approximately one-third of the sky. The survey used a dedicated 2.5-meter telescope at Apache Point Observatory in New Mexico, equipped with specialized instruments capable of simultaneously measuring spectra for hundreds of galaxies. Fibers positioned at galaxy locations feed light to spectrographs, enabling efficient multi-object spectroscopy. Each clear night produced hundreds or thousands of galaxy spectra, gradually building a three-dimensional map spanning billions of light years. The resulting catalogue revolutionized cosmic structure studies, revealing the cosmic web in unprecedented detail and enabling discoveries including the Sloan Great Wall and detailed characterizations of voids, filaments, and superclusters. Photometric redshifts provide distance estimates without spectra using multi-wavelength imaging. By photographing the same sky region through multiple filters spanning ultraviolet to infrared wavelengths, astronomers measure each galaxy's spectral energy distribution. Comparing observed colors to templates representing galaxies at different redshifts estimates photometric redshift with typical uncertainties around 3 to 5%. This technique is less accurate than spectroscopic redshift, but applicable to fainter galaxies where obtaining spectra is impractical. Surveys like the Dark Energy Survey and future missions including Euclid and the Vera Rubin Observatory will use photometric redshifts to map billions of galaxies, creating the largest cosmic structure catalogues ever assembled. Peculiar velocity measurements reveal gravitational influences by detecting deviations from smooth Hubble expansion. A galaxy's total velocity has two components: recession from cosmic expansion plus peculiar velocity from gravitational attractions. Measuring peculiar velocities requires independent distance estimates, not based on redshift. Techniques include using Tully-Fisher relation for spirals, where rotation velocity correlates with intrinsic luminosity, or fundamental plane relation for ellipticals, where velocity, dispersion, and size correlate with luminosity. Comparing true distance from these methods to distance inferred from redshift reveals peculiar velocity. The Cosmic Flows project has measured peculiar velocities for thousands of galaxies, mapping velocity flows that defined Laniakea and revealed large-scale gravitational influences from the Great Attractor and Shapley concentration. Gravitational lensing maps dark matter distribution independent of light from galaxies. When massive structures like galaxy clusters lie between Earth and more distant sources, their gravity bends light, distorting background galaxy images. Weak lensing produces subtle distortions in galaxy shapes, coherent patterns revealing foreground mass distribution. Measuring shears requires precise shape measurements for millions of background galaxies. Statistical analysis, detecting correlations, indicating lensing. Strong lensing produces dramatic effects, including multiple images or arcs, allowing detailed mass modeling. Lensing surveys like the Kilodegree Survey and Dark Energy Survey have mapped dark matter across thousands of square degrees, revealing how dark matter filaments connect galaxy clusters and how dark matter distribution relates to visible structure. The cosmic microwave background provides a different perspective on cosmic structure, showing the universe at recombination when structure was still in early stages. The CMB's temperature variations, approximately 1 part in 100,000 across the sky, represent density fluctuations that would later grow into galaxies and large-scale structure. The fluctuation pattern's statistical properties constrain cosmological parameters, including matter density, dark energy, and the primordial fluctuation spectrum. Missions, including COBE, WEMAP, and Planck, measured the CMB with progressively improving precision, determining cosmological parameters to percent-level accuracy. These measurements provide initial conditions for structure formation, complementing galaxy surveys, showing the endpoint of structure growth. Combining multiple techniques creates comprehensive structure maps. Galaxy surveys provide galaxy positions. Redshift surveys add distances, creating three-dimensional distributions. Peculiar velocities reveal gravitational dynamics. Lensing maps dark matter, and CMB shows initial conditions. Integrating these datasets tests whether observations consistently fit cosmological models. Do galaxy distributions match dark matter maps? Do peculiar velocities match gravitational accelerations inferred from galaxy clustering? Does the CMB power spectrum predict large-scale structure-matching observations? Agreement across techniques strengthens confidence in our understanding. Disagreements identify where models need refinement or observations require improvement. Future surveys will dramatically improve cosmic structure measurements. The Vera Rubin Observatory's Legacy Survey of Space and Time will photograph the entire southern sky every few nights for 10 years, creating a time-lapse movie of the universe while obtaining photometric redshifts for billions of galaxies. Euclid will map galaxy shapes and redshifts across 1/3 of the sky, measuring gravitational lensing and galaxy clustering with unprecedented precision. The Nancy Grace Roman Space Telescope will conduct deep surveys measuring galaxy properties to high redshift, tracing structure evolution across cosmic time. Ground-based spectroscopic surveys, including DESI, the Dark Energy Spectroscopic Instrument, will measure redshifts for tens of millions of galaxies. These observations will map cosmic structure with detail impossible in previous generations, testing cosmological models with percent-level precision. Analyzing cosmic structure requires sophisticated statistical techniques, extracting maximum information from observations. The two-point correlation function measures galaxy clustering strength versus separation, quantifying how galaxies cluster on different scales. The power spectrum, the correlation function's Fourier transform, describes fluctuation amplitude versus scale, connecting observations to theory, predicting structure from initial fluctuations. Higher-order statistics, including 3-point and 4-point functions, reveal non-Gaussian features providing additional constraints. Machine learning techniques are increasingly applied, using neural networks to classify galaxies, identify structures, measure redshifts, and model complex relationships. These tools transform raw observations into cosmological constraints, revealing the universe's structure and testing theoretical understanding. The limits of structure: how big can structures get? The question of maximum structure size connects to fundamental cosmological principles and physical constraints, limiting how large coherent structures can grow given the universe's finite age and accelerating expansion. The cosmological principle states that the universe should appear homogeneous and isotropic on sufficiently large scales, typically cited as approximately 300 million light-years, beyond which statistical fluctuations should average out, leaving uniform density. Observations broadly confirm this, showing that structure amplitude decreases on larger scales, with the cosmic web's pattern becoming less prominent. However, structures approaching or potentially exceeding 1 billion light-years challenge naive interpretations of this principle, raising questions about whether observed large structures are genuine, coherent formations or statistical fluctuations in galaxy distributions. The particle horizon at recombination, representing the maximum distance over which regions could have been in causal contact when the cosmic microwave background formed, sets a fundamental scale. At recombination 380,000 years after the Big Bang, the horizon size was approximately 1 million light-years in co-moving coordinates. Regions, separated by more than this distance, could not have influenced each other because light from one had insufficient time to reach the other. This horizon scale is much smaller than observed large structures, seemingly preventing their formation through coordinated processes. Cosmic inflation solves this paradox by proposing that all currently observable regions were in causal contact before inflation stretched them to enormous separations. Post-inflation, quantum fluctuations generated during inflation created correlated density variations across vast scales, providing the seeds for large-scale structure. The sound horizon at recombination, approximately 450,000 light-years in co-moving coordinates, represents the distance sound waves traveled through the photon-baryon plasma before recombination. This scale is imprinted in the cosmic microwave background as the acoustic peaks, and in galaxy distributions as baryon acoustic oscillations. A characteristic scale visible in galaxy clustering around 500 million light-years. Structures significantly larger than the sound horizon at recombination require explanations beyond simple acoustic evolution, typically involving gravitational amplification of larger scale fluctuations generated during inflation. The largest fluctuations observable in the CMB correspond to scales approaching the observable universe's size at recombination, setting an upper limit on structure scales seeded directly by quantum fluctuations during inflation. Gravitational growth timescales limit how quickly structures can form through matter collapse. Structures form when initially overdense regions stop expanding, reach maximum size, then collapse under self-gravity, virializing into bound systems. The timescale for this process is the gravitational timescale, roughly 1 over square root of density times gravitational constant. For cosmic average density, this timescale is comparable to the universe's age, meaning structures at average density are just beginning to collapse. For structures to be fully formed and virialized today, they must have started with sufficient overdensity that their local gravitational timescale was much shorter than cosmic age. This requirement limits how massive structures can grow given available time since the Big Bang. Dark energy complicates structure formation by driving accelerated expansion beginning approximately 5 billion years ago. Before dark energy dominated, matter's gravity slowed expansion, allowing structures to continue growing. Once dark energy dominated, accelerated expansion works against gravitational collapse on large scales. Structures smaller than approximately 10 to 20 million light-years, where internal gravity exceeds dark energy's repulsive effect, remain bound and continue growing through accretion and mergers. Larger structures cannot overcome accelerated expansion and fail to collapse into bound systems. Superclusters like Laniakea and the Shapley concentration are not gravitationally bound as single units, but represent transient density enhancements that will gradually disperse as expansion continues. The transition scale between bound clusters and unbound superclusters roughly marks the maximum size for structures that will persist into the far future. Statistical considerations affect how we interpret large structures. In any finite volume, random fluctuations occasionally produce large density enhancements purely by chance. The question is whether observed large structures represent rare but expected statistical fluctuations or indicate something wrong with our models. The probability of finding a structure of given size and overdensity can be calculated from the density fluctuation spectrum measured in the cosmic microwave background. Structures like the Sloan Great Wall at 1.4 billion light-years represent approximately 3 sigma fluctuations, rare but expected to occur occasionally in the observable universe's volume. Structures approaching 10 billion light-years, like the claimed Hercules Corona Borealis Great Wall, would represent 5 sigma or higher fluctuations. So rare that finding even one in the observable universe is surprising, raising questions about whether such structures are genuine or reflect observational biases. The maximum structure size might be set by the cosmic web's topology rather than by simple gravitational constraints. Simulations show that the cosmic web naturally produces filaments and walls, extending several 100 million light-years, with the largest continuous filaments reaching perhaps 1 to 2 billion light-years. These structures are not gravitationally bound, but represent statistical enhancements in galaxy density along preferential directions determined by the large-scale velocity field. The longest filaments form where multiple smaller filaments happen to align, creating apparent continuity over enormous distances. Whether such aligned structures should be considered single coherent formations or chance alignments of independent structures is partly definitional. Different criteria produce different maximum sizes, illustrating that structure size is somewhat ambiguous for the cosmic web's largest features. Observations at high redshift constrain structure size evolution by showing the universe at earlier epochs when structures were smaller and less developed. At redshift 2, corresponding to cosmic time when the universe was 3 billion years old, the cosmic web was less prominent, with smaller filaments and walls. The largest structures at that epoch measured several 100 million light-years, smaller than today's billion light-year structures. This evolution demonstrates that structure grows with time, consistent with gravitational amplification predictions. Extrapolating backward, we find that structure size approaches zero at very high redshift approaching the Big Bang, as expected if structure grows from tiny initial fluctuations. This consistency supports our understanding of structure formation while confirming that observed large structures represent the endpoint of billions of years of gravitational evolution. Future observations will better determine maximum structure sizes by mapping the universe to greater distances with improved completeness. As surveys become larger and more sensitive, they detect more galaxies across larger volumes, potentially revealing even larger structures or confirming that billion light-year scales represent true maxima. Comparing observed structure abundance versus size to theoretical predictions tests to cosmological models. Finding more large structures than predicted might indicate that initial fluctuations were larger than inferred from the CMB, that structure formation proceeded faster than standard models predict, or that dark energy behaved differently in the past. Finding fewer large structures would be less problematic, potentially indicating that some reported large structures are not genuine. Either outcome provides valuable constraints on cosmic structure formation and fundamental cosmological parameters. Future evolution of cosmic structures' dark energy's influence. Cosmic structures, as we observe them today, represent a transitional phase in the universe's evolution. Neither the uniform plasma of the early universe, nor the dispersed, isolated clusters of the far future. Understanding how structures will evolve requires accounting for dark energy's accelerating expansion, which has dominated cosmic dynamics for approximately 5 billion years and will increasingly shape the universe's future. Dark energy prevents new large-scale structure formation and will gradually disperse existing structures larger than galaxy clusters, eventually isolating bound systems in an ever-expanding void. Tracing this evolution reveals the universe's ultimate fate, not catastrophic collapse, but gradual thinning, as expansion without bound carries structures beyond each other's cosmic horizons. The immediate future, over the next 10 to 100 billion years, will see continued structure evolution through mergers and accretion. Galaxy clusters will continue growing as smaller groups fall into them along cosmic web filaments. The local groups merger with nearby groups will create larger bound systems. The Milky Way and Andromeda will collide and merge within approximately 4 to 5 billion years, creating an elliptical galaxy. The Triangulum galaxy and dozens of dwarf members will also merge into this system, producing a single massive galaxy containing several trillion stars. Similar mergers will occur throughout the universe as galaxy groups consolidate. These mergers represent structure evolution on small scales where gravity overcomes expansion, growing bound systems, while cosmic expansion carries more distant regions apart. Galaxy clusters will remain bound despite accelerated expansion because their internal gravity exceeds dark energy's repulsive effect on scales below approximately 10 to 20 million light-years. Clusters will continue accreting galaxies and groups from surrounding regions, growing in mass and size. However, the infall rate will decrease as expansion accelerates, reducing the supply of new material. Eventually, within approximately 100 billion years, clusters will have accreted all galaxies within their gravitational reach, with more distant galaxies receding beyond recovery. Clusters become isolated island universes, each containing thousands of galaxies bound together but separated from other clusters by ever-growing distances as expansion continues. Superclusters like Laniakea and Shapley, will disperse because they are not gravitationally bound. While current observations show coherent flows where galaxies move towards supercluster centers, these motions cannot overcome long-term expansion acceleration. Over tens of billions of years, the coherent flows will weaken as dark energy increasingly dominates over gravitational attraction on 100 million light-year scales. Superclusters will fragment as constituent clusters and groups separate, each following cosmic expansion with peculiar velocities too small to maintain connections. The cosmic web's filaments and walls will thin and fade as galaxies and groups composing them drift apart. Within approximately 150 billion years, the cosmic web as a coherent structure will have dissolved, leaving isolated galaxy clusters separated by vast voids. The cosmic event horizon, currently located at approximately 16 billion light-years, separates regions we can potentially reach from regions forever beyond contact. Objects beyond this horizon recede faster than light due to expansion, meaning signals emitted toward us can never arrive because expansion carries them away faster than they approach. As expansion accelerates, the event horizon contracts in comoving coordinates, meaning progressively more objects cross beyond it. Currently, approximately 95% of galaxies in our observable universe lie beyond the event horizon. We see them only because we observe ancient light emitted billions of years ago when they were inside our past event horizon. Their present states are forever hidden, and over time, even their ancient light will redshift beyond detection. Observers in the far future will see increasingly empty skies as galaxies beyond the local group cross the event horizon and disappear. Within 150 billion years, all external galaxies will have vanished from view, leaving only the merged local group galaxy and perhaps a few very nearby groups visible. The cosmic microwave background will have cooled to temperatures below detection thresholds, its photons stretched to wavelengths exceeding light years. Future observers will see only their local galaxy in an otherwise empty universe, with no evidence of the billions of galaxies that once populated the cosmos. They will lack observational evidence for the Big Bang, cosmic expansion, or the existence of other galaxies, potentially making it impossible to infer cosmological truth from observations alone. Star formation will continue in merged galaxies for tens to hundreds of trillions of years as remaining gas is consumed. Low-mass red dwarf stars, the longest-lived stellar type, will continue shining for trillions of years after more massive stars have died. The last red dwarfs will exhaust hydrogen fuel approximately 100 trillion years from now, marking the end of the stelliferous era, the epoch of shining stars. After this, no new stars form anywhere. The universe transitions to the degenerate era, containing only stellar remnants, white dwarfs cooling toward absolute zero, neutron stars radiating residual heat, brown dwarfs that never ignited fusion, gradually cooling, and black holes slowly evaporating through Hawking radiation. Cosmic structure in the far future consists of isolated remnant galaxies, separated by cosmological distances, growing without bound. Within each remnant galaxy, stellar remnants drift in orbits around central supermassive black holes. Over timescales exceeding 10 to the 19th years, gravitational encounters between remnants cause some to merge while ejecting others from galaxies entirely. Galaxies gradually evaporate, losing stars through this process until only dense cores remain around central black holes. If protons decay, as some theories predict, all matter composed of protons disintegrates over 10 to the 36th years, dissolving white dwarfs, neutron stars, and planets into electrons, positrons, neutrinos, and radiation. Only black holes persist as significant mass concentrations. Black holes evaporate through Hawking radiation over timescales, scaling as mass cubed. A solar mass black hole evaporates in approximately 10 to the 67th years. A million solar mass black hole persists for 10 to the 83rd years. The largest supermassive black holes, billions of solar masses, evaporate around 10 to the 100th years. After the last black holes evaporate, the universe enters the dark era, the final epoch approaching heat death. Only an extraordinarily dilute bath of photons, neutrinos, and possibly electrons persists at temperatures approaching absolute zero. Cosmic structure has completely dissolved. No galaxies, no clusters, no filaments, nothing but diffuse radiation and particles stretched to infinite wavelengths by endless expansion. This future represents thermodynamic death, not through destruction, but through maximum entropy. The universe continues existing, but nothing happens. Energy is distributed uniformly at minimum temperature. Expansion continues, diluting matter and energy further, but the dilution produces no changes because everything is already maximally dispersed and cooled. Time becomes operationally meaningless because no processes occur to mark its passage. The cosmic structures we observe today, galaxies, clusters, filaments, superclusters, are temporary configurations existing during a brief window when the universe is old enough for gravity to have organized matter, but young enough that dark energy has not yet dispersed all structures beyond mutual contact. We observe cosmic architecture during its prime, before accelerating expansion erases all structure and reduces the universe to cold, dark, infinite void. Our place in the cosmic architecture. Understanding the universe's largest structures provides profound perspective on our place in the cosmos. The local group occupies the outskirts of Laniakea supercluster, one velocity flow basin among many populating the cosmic web spanning the observable universe. Our supercluster, while enormous at 520 million light-years across, represents only one structure among countless similar formations distributed throughout space. The Milky Way, containing hundreds of billions of stars and stretching 100,000 light-years, is merely one galaxy among the 100,000 galaxies in Laniakea, which itself contains only a tiny fraction of the estimated 2 trillion galaxies in the observable universe. This hierarchical diminishment, from cosmic scales to human scales, could seem to render us insignificant. Yet the very ability to comprehend these scales represents something remarkable in the universe's story. The Milky Way's position within Laniakea is peripheral rather than central. We reside approximately 250 million light-years from the supercluster's center of mass near the Great Attractor region in a relatively underdense area between major filaments. This location is neither privileged nor special. Most galaxies in any supercluster occupy similar intermediate density environments rather than dense cluster cores or empty voids. The Copernican principle, stating that we do not occupy a special position, continues to hold even on supercluster scales. Our location appears ordinary, representative of typical environments within cosmic structure. This ordinariness itself provides valuable perspective. The universe we observe from our vantage point likely resembles what observers in other galaxies, other groups, other superclusters would observe from their positions. Understanding cosmic structure, evolution, reveals our temporal position in universal history. The universe is currently 13.8 billion years old, approximately 1/3 through its star-forming era if star formation continues for another 50 to 100 trillion years before gas exhaustion. We exist during the epoch when cosmic structure is most prominent, the cosmic web fully developed, galaxy clusters mature, but acceleration has not yet dispersed superclusters beyond observability. Observers in the far future will see emptier skies as structures disappear beyond event horizons. Observers in the early universe would have seen less developed structure with smaller galaxies and protoclusters. We inhabit a sweet spot where the universe is old enough for complexity to develop, but young enough that complexity remains visible and accessible. The cosmic web's structure demonstrates that we are not just residents of a galaxy, but inhabitants of a vast interconnected system extending hundreds of millions of light years. The local group belongs to a chain of structures including the Virgo cluster, the Great Attractor region, and the Shapley concentration, all connected through gravitational dynamics and matter flows. Our motion through space at 630 kilometers per second relative to the cosmic microwave background results from the combined gravitational influences of these structures, demonstrating that even our velocity reflects our cosmic neighborhood's architecture. We are not isolated, but embedded in a network of gravitational relationships extending across Laniakea and beyond. Studying cosmic structure reveals the universe's governing principles while testing our understanding of fundamental physics. The cosmic web's properties constrain dark matter's nature, dark energy's behavior, gravity's laws across enormous scales, and the validity of our cosmological models. Every measurement refining structure's properties, cluster masses, filament lengths, void sizes, supercluster boundaries, tests theoretical predictions, and potentially reveals new physics. The fact that observations broadly match predictions from standard cosmology, combining general relativity, quantum mechanics, and the standard model of particle physics demonstrates that our understanding extends successfully from laboratory scales to cosmic scales spanning billions of light years. The question of life's prevalence in these vast structures remains unanswered. Earth is the only known location harboring life despite observations of thousands of exoplanets and the estimated existence of billions of potentially habitable worlds in our galaxy alone. The Fermi paradox asks, if intelligent life is common, where is everyone? The cosmic web's enormous scale makes this question more acute. If civilizations exist elsewhere, vast distances separating galaxies, clusters, and superclusters render contact extraordinarily difficult, even if civilizations are common. Light requires millions to hundreds of millions of years to cross intergalactic and supercluster scales. The cosmic expansion carries distant structures beyond communication reach. We might be one civilization among billions, distributed across cosmic structures, yet forever isolated by distance and expansion, each developing independently without knowledge of others. Alternatively, we might be rare or unique within observable volume. If life requires exceptionally specific conditions, the observable universe's 2 trillion galaxies might contain only thousands, hundreds, or even fewer instances of intelligent life. Earth might represent a cosmic rarity, a place where matter organized into complexity, consciousness, and intelligence, despite enormous odds against such organization. From this perspective, understanding cosmic structure takes on added significance. We are products of 13.8 billion years of cosmic evolution, from quantum fluctuations during inflation through gravitational structure formation to galaxy formation, stellar evolution, planet formation, and biological evolution. We are the universe examining itself, structure that became conscious, capable of comprehending the architecture surrounding us. Ultimately, our place in cosmic structure represents a profound juxtaposition between scale and significance. We occupy an ordinary galaxy in an ordinary position within an ordinary supercluster, physically insignificant against the cosmic web's vastness. Yet we are the only known observers, the only location where matter has organized sufficiently to ask questions about cosmic architecture and comprehend answers spanning billions of light years. This combination of spatial insignificance and intellectual capability defines the human condition in cosmic context. Tiny in extent but vast in understanding, brief in duration but curious about eternity, local in location but capable of imagining and mapping the entire observable universe, from quantum fluctuations to cosmic web to heat death. The largest structures in the universe are incomprehensibly enormous, and we are infinitesimally small, yet somehow we have measured them, modelled them, and understood them. That achievement, perhaps more than anything, defines our place in the cosmic architecture